Reality has always felt stable to us. The ground beneath our feet seems solid. The sky above appears endless yet consistent, and the flow of time feels like a straight line. Our everyday experience convinces us that the world operates according to rules that never fail. But when scientists began probing beneath the surface of ordinary matter, they uncovered something that shook this confidence to its core. At the smallest levels of existence, reality does not behave the way we expect. It bends, twists, and resists simple explanation. Out of this resistance arises something more than confusion. What we discover at the quantum scale is not merely complicated, it is paradoxical. A paradox is more than a puzzle. It is a contradiction that should not exist, yet does. It points to a crack in the very logic we use to make sense of the world. When philosophers wrestle with paradoxes, they challenge language and reasoning. But when physicists collide with paradoxes, they confront the possibility that nature itself refuses to conform to human expectations. The paradox that concerns us here, the one that hovers at the edge of reality, goes beyond a curiosity. It threatens the foundation of existence. If true, it could reveal that the very rules of the universe contradict themselves. If false, it suggests we still do not understand what reality is made of. Either way, it demands attention. This paradox begins with the discovery that, on the quantum scale, matter is not as simple as particles colliding like billiard balls. Instead, electrons, photons, and the fundamental building blocks of nature behave as though they are both particles and waves. They occupy positions and states only when observed, and until then, they remain suspended in possibilities. This is not metaphorical or poetic. It is verified in countless experiments, repeated across decades of research. The results are unavoidable. Reality does not exist in a definite way until it is measured. That realization introduces a problem no physicist has ever solved. What does it mean for the universe if things are not real until we look at them? Imagine building a house. You lay the foundation, erect the walls, and put on a roof. Each brick is real. Each nail is hammered into wood that occupies space. Now picture a universe where those bricks, nails, and beams only exist when you check on them. If you turn away, they dissolve into probabilities. Not quite real, but not gone either. They hover in a shadow state, waiting for attention to bring them into being. This is not science fiction. This is the conclusion that follows from quantum experiments. And if that conclusion is correct, then reality is not independent of us. It is entangled with our act of observing. The paradox sharpens here. If reality needs to be observed to exist in a definite way, then who or what observed the universe before conscious beings arrived? The cosmos is 13.8 billion years old. Stars formed, galaxies collided. Black holes grew at the centers of spirals long before life emerged on Earth. Was the universe suspended in a haze of probabilities until eyes evolved to witness it? That cannot be the case. And yet experiments suggest something disturbingly close to it. Either consciousness plays a role in shaping reality, or there is a hidden mechanism that we have not yet uncovered. Both options threaten the framework of physics as we know it. This is the paradox at the edge of reality. On one side, the traditional view holds that the universe is objective. It exists whether or not anyone is watching, independent of perception. On the other side, quantum mechanics suggests that outcomes only become definite when measured. The clash between these views has no easy resolution. If the quantum description is correct, then our ordinary picture of the universe collapses. The solidity of matter, the sequence of cause and effect, the very idea that reality is stable all become questionable. If the traditional view is correct, then we must explain why experiments consistently contradict it. Either way, we stand before a contradiction that breaks the boundary between what we think is real and what the evidence demands. Scientists, philosophers, and thinkers have proposed many ways to escape this trap. Some argue that hidden variables, undiscovered pieces of physics, explain the strangeness. Others claim that multiple universes branch off at every decision. So reality remains objective, but spreads infinitely. Still others suggest that consciousness itself is woven into the physics of the cosmos, and that mind and matter cannot be separated. Each explanation tries to resolve the paradox, but none have eliminated it. The questions remain open, echoing through every laboratory and every lecture hall that deals with quantum foundations. The paradox matters because it forces us to confront what real even means. In daily life, reality feels unquestionable. A table is a table, a tree is a tree, and you do not worry that they vanish when you leave the room. Yet if quantum mechanics is taken seriously, those certainties are illusions. The table is a cloud of probabilities, stabilized only when engaged with. The tree is not a definite object, but a set of quantum possibilities, aligned into form by the act of existence itself. What is more unsettling is that physics cannot yet explain why this works. We know it happens. We can measure the effects, calculate them with exquisite precision, and build technologies like lasers and transistors from them. But the interpretation, the meaning behind the math still eludes us. And so we arrive at the edge of reality, where physics meets philosophy, and both tremble before the same abyss. The paradox is not just a puzzle for academics. It reverberates into every human attempt to understand existence. If the paradox is resolved one way, it may mean that the universe is alive with hidden layers of information and possibility. If resolved another way, it may reveal that we are participants in shaping the cosmos through observation. And if left unresolved, it may mean that reality itself is inherently contradictory, that the foundation of existence is built upon a contradiction it cannot escape. This is the journey we are beginning, to follow the paradox from its origins to its implications, to understand how it arose, and to explore what it means for the nature of everything. It is a path that will lead through experiments, theories, and daring ideas that stretch human imagination. Along the way, we will discover not only the strangeness of the quantum world, but also the unsettling possibility that reality itself is far more fragile than we ever imagined. At the dawn of the 20th century, science stood on a foundation that seemed unshakable. Newton's laws had described the motions of planets and falling apples with unmatched precision for over 200 years. Maxwell's equations had unified electricity, magnetism, and light into a single elegant framework. Engineers could design bridges, build steam engines, and send signals through wires with full confidence that nature was predictable. For most scientists of the late 19th century, it appeared as if physics was nearing completion. The remaining tasks seemed like mere fine-tuning, filling in the last small details of a nearly finished picture. But that confidence did not survive the turn of the century. In laboratories across Europe, subtle cracks began appearing in the classical framework. They did not seem catastrophic at first, quirks in data, minor mismatches between theory and experiment. Yet each crack widened until the entire structure of physics shook. From these cracks emerged the beginnings of quantum theory, and with it, the paradoxes that still haunt us today. The first major tremor came in 1900, when Max Planck attempted to solve what was called the problem of blackbody radiation. Classical physics predicted that a heated object should emit light with infinite energy at high frequencies, a nonsensical conclusion known as the ultraviolet catastrophe. Experiments clearly showed that real objects glowed in a specific way, peaking in the visible range and tapering off at higher frequencies. Planck struggled with the equations until, in desperation, he introduced an audacious idea. Energy is not continuous. It comes in discrete packets, which he called quanta. This was not meant as a revolution. Planck himself considered it a mathematical trick to make the equations fit. But that trick worked, and it fit so perfectly that it could not be ignored. By slicing energy into indivisible chunks, he resolved the catastrophe and matched experiment with theory. What Planck did not realize immediately was that he had cracked open the door to an entirely new world. The assumption that energy flows smoothly had been abandoned, and in its place was a strange, grainy universe where nature took discrete steps, rather than continuous strides. Soon after, Albert Einstein expanded on this radical shift. In 1905, he published a paper explaining the photoelectric effect, in which light striking a metal surface knocks electrons free. Classical physics predicted that the energy of the electrons should depend on the brightness of the light, but experiments showed it depended instead on the frequency. Einstein proposed that light itself was quantized, composed of particles we now call photons. By treating light as a stream of quanta rather than a continuous wave, he explained the observations precisely. This was shocking. For centuries, experiments had demonstrated light's wave-like properties: diffraction, interference, reflection. Now Einstein was telling the world that light could also act as a particle. The contradiction was clear. Was light a wave or a particle? The unsettling answer would eventually be both, depending on how you looked at it. The neat categories of classical physics were beginning to dissolve. While Einstein and Planck were reshaping our understanding of light and energy, Niels Bohr was confronting another puzzle: the structure of the atom. According to classical physics, electrons orbiting a nucleus should radiate energy continuously, spiraling inward until the atom collapses. Yet atoms clearly exist, and they are stable. Bohr solved this by borrowing from Planck's quantum idea. He suggested that electrons could occupy only certain discrete energy levels, jumping between them in sudden transitions while emitting or absorbing quanta of light. His model, though crude, explained the spectral lines observed when atoms were excited. The Bohr model was an uneasy hybrid of classical mechanics and new quantum ideas. It worked, but it raised uncomfortable questions. Why should electrons be restricted to specific orbits? Why were these jumps instantaneous? And what exactly was the mechanism that governed such transitions? No one had answers. The theory was useful, yet mysterious. As the 1920s unfolded, the mysteries multiplied. Werner Heisenberg, Erwin Schrödinger, and Paul Dirac developed more sophisticated formulations of quantum mechanics. Heisenberg's matrix mechanics and Schrödinger's wave mechanics seemed radically different, but turned out to be equivalent descriptions of the same strange reality. Schrödinger's wave function described particles not as tiny balls moving through space, but as smeared-out probabilities existing in superpositions of states until measured. Heisenberg's uncertainty principle declared that certain pairs of properties, like position and momentum, could never be known simultaneously with arbitrary precision. These were not small adjustments to classical physics. They were radical departures. The familiar clockwork universe of Newton had been replaced by something fluid, probabilistic, and deeply unsettling. Measurement itself seemed to play a central role in determining outcomes. Observation was no longer passive. It was active, shaping what could be known. For Einstein, this was intolerable. He famously resisted the notion that the universe was governed by chance, remarking, "God does not play dice." He sought hidden variables, unseen factors that would restore determinism and objectivity. Bohr, on the other hand, defended the new view passionately, insisting that quantum mechanics was complete and that paradox was not a flaw but a feature of nature. Their debates, carried out over decades, shaped the very language of physics. What makes this era so important is not only the discoveries themselves, but the way they cracked open the idea of certainty. Each experiment peeled away another layer of classical expectation. Energy was not continuous. Light was not purely a wave. Atoms were not miniature solar systems. Particles did not have definite properties until observed. The seeds of paradox had been planted, and they were already beginning to grow. By the end of the 1920s, quantum mechanics was not merely a theory. It was a revolution. It explained phenomena that classical physics could not touch, from the stability of matter to the behavior of semiconductors. It laid the groundwork for technologies that would transform the modern world. But beneath its triumphs lurked questions that no one could answer. Why does observation collapse possibilities into outcomes? What does it mean for a particle to exist in a superposition? If reality is built from probabilities, what anchors it into something definite? These were not trivial details. They were fractures in the very concept of reality. The paradoxes were no longer confined to blackboards and equations. They were real, and they would not go away. From Planck's desperate trick to Einstein's photons, from Bohr's atoms to Schrödinger's waves, the early decades of the 20th century reshaped science and revealed a universe far stranger than anyone expected. The classical world had cracked, and through those cracks, the quantum paradox began to emerge. When scientists first began to study matter and energy at their most fundamental levels, they expected to find simplicity. Atoms, electrons, photons, these building blocks were supposed to behave like the solid bricks of the universe, each one distinct and predictable. But what emerged from the experiments of the early 20th century was not a neat, orderly picture. Instead, the foundations of matter revealed themselves to be shape-shifting, as if nature could not decide whether it wanted to act like a wave or a particle. This puzzling behavior, known as wave-particle duality, became one of the most unsettling discoveries in science and remains the cornerstone of quantum strangeness. To understand how extraordinary this is, it helps to recall what waves and particles mean in the classical world. A particle is a localized object, something with a position in space. A grain of sand, a billiard ball, or even a planet can be thought of as particles entities that occupy a specific place and move along a defined path. Waves, on the other hand, are extended and continuous. A ripple in a pond, a sound moving through air, or light traveling as an electromagnetic oscillation are all examples of waves. Waves spread out, interfere with one another, and combine into patterns. Particles collide and scatter, but they do not overlap in the way waves do. In everyday experience, these two categories are distinct. You do not mistake a rock for a ripple, or a water wave for a marble. Yet in the quantum world, nature refuses to remain within those boundaries. Light, once thought of as a wave, revealed particle-like behavior in the photoelectric effect. Electrons, which were long considered particles, began to show unmistakable signs of wave-like behavior. This duality is not a matter of misunderstanding. It is an experimental fact, verified countless times. One of the first dramatic demonstrations came in experiments with electrons. In 1927, Clinton Davison and Lester Germer at Bell Labs conducted a study in which they fired electrons at a crystal of nickel. Instead of scattering randomly, the electrons formed distinct interference patterns, exactly as waves of light do when they pass through a diffraction grating. This was not a fluke. The pattern could only be explained if electrons were behaving like waves, spreading out and overlapping before forming bright and dark bands of interference. The implications were staggering. Electrons had always been considered particles, discrete bits of matter carrying charge. Yet here they were, displaying interference patterns that belonged to waves. Louis de Broglie had predicted this strange behavior a few years earlier, suggesting that matter itself has wave-like properties. The Davison-Germer experiment confirmed it, and the world had to accept the impossible. Matter could act like a wave. This duality became even more bewildering when scientists realized it was not limited to electrons. Protons, neutrons, even entire atoms all displayed wave-like behavior under the right conditions. The very objects we think of as solid matter were capable of interference, diffraction, and superposition, all hallmarks of waves. And yet, when measured in a different way, the same entities revealed themselves as particles, striking detectors one by one, like tiny bullets. How could something be both? The logic of classical physics had no room for such contradictions. If an object is a wave, it should spread continuously through space. If it is a particle, it should be localized and distinct. But quantum experiments refused to choose. Nature insisted on showing both faces, depending on how we looked. To make sense of this, physicists developed mathematical tools rather than intuitive pictures. Schrödinger's wave equation described particles as wave functions extended across space, evolving according to strict rules. But when measured, the wave functions seemed to collapse into a specific outcome, as if the particles suddenly decided to act localized. Before measurement, the entity behaved like a wave, capable of being in many places at once. After measurement, it presented itself as a single, definite particle. This created a tension that has never been resolved. What is the true nature of reality before measurement? Is the electron really spread out as a wave, or is the wave function just a description of probabilities? Does the particle exist only as a potential until we interact with it? The duality does not answer these questions. It merely highlights the paradox. For many scientists, the wave-particle duality is not just a curiosity, but a profound clue. It suggests that our categories of wave and particle are human constructs, inadequate to describe the quantum world. Reality may not fit into the neat boxes we inherited from classical physics. Instead, it may operate according to principles that defy ordinary logic, principles that only reveal themselves through mathematics and experiment. Yet the paradox does not stop at theory. Wave-particle duality underlies the technologies that define modern life. Without it, semiconductors would not work, lasers would not exist, and quantum computers would be impossible. Our ability to harness duality for practical use does not mean we understand it. We have learned to manipulate the paradox, but the mystery remains untouched. The unsettling part is that duality is not optional. It is not a mistake of measurement or a quirk of experiment. It is fundamental to the way the universe behaves. If matter and energy refused to exhibit dual properties, atoms would not form, and reality as we know it could not exist. The very fabric of existence is paradoxical, woven from contradictions that refuse to be reconciled. Wave-particle duality is the first clear glimpse into a reality that refuses to stay consistent under observation. It shows us that the universe is not a stable machine of definite objects, but a shifting tapestry of possibilities, collapsing into outcomes only when forced. It is the foundation of quantum mechanics, and it is the doorway through which all other paradoxes emerge. Once scientists accepted that duality was unavoidable, they opened themselves to even stranger conclusions that continue to challenge the very meaning of reality itself. If there is one experiment that captures the bizarre essence of quantum mechanics, it is the double-slit experiment. It is elegant in its design, deceptively simple in its setup, yet it exposes a fracture in our understanding of the universe so profound that it unsettles even the most seasoned physicists. This experiment is where the wave-particle duality we encountered earlier reveals its full paradoxical nature, and it is also where the role of observation enters the story in a way that defies conventional logic. The idea dates back to Thomas Young in the early 19th century, when he sought to prove that light behaved as a wave. His apparatus was straightforward. Shine light at a barrier with two narrow slits, then observe what appears on a screen behind it. If light were composed of particles, as Isaac Newton once believed, you would expect to see two bright bands corresponding to the slits, much like paintballs hitting a wall. But what Young observed was something very different, an interference pattern of alternating light and dark bands. The light waves from the two slits overlapped, producing regions of reinforcement and cancellation. It was conclusive proof that light behaved as a wave. More than a century later, with the rise of quantum mechanics, physicists repeated the experiment under new conditions. Instead of light, they fired electrons' tiny particles of matter at the slits. To their astonishment, electrons, like light, produced the same interference pattern, even when fired one at a time. with long gaps between each particle. The cumulative result still formed a wave-like distribution. Each electron seemed to pass through both slits simultaneously, interfering with itself as though it were a wave spread out across space. The conclusion was unavoidable. Matter behaved like a wave in this context. But the real paradox emerged when scientists asked a seemingly innocent question. What path does each electron take? If the electron is a particle, then surely it must travel through one slit or the other. To find out, detectors were placed at the slits to observe which path each electron chose. At that moment, the experiment shifted into something deeply unsettling. With detectors in place, the interference pattern disappeared. The electrons no longer behaved like waves. They behaved like particles, producing two bands on the screen instead of many. Observation itself had changed the outcome. This result is one of the most confounding discoveries in all of physics. Without observation, electrons spread out like waves, creating interference. With observation, they collapse into definite paths, behaving like particles. The act of measurement altered reality, as if the universe were aware of being watched. No adjustment of equipment or reinterpretation of the data could erase the fact that observation changed the fundamental behavior of matter. The implications are staggering. If particles can exist in a superposition of possibilities, traveling through both slits at once, then reality at the quantum level is not definite until forced into definition. But what forces that definition? Is it the physical act of detection, the interaction with a measuring device, or is consciousness itself required to finalize the outcome? These questions remain unresolved, and they form the heart of the quantum paradox. Physicists have tried to interpret the double-slit experiment in many ways. The Copenhagen interpretation, championed by Niels Bohr, argues that quantum systems exist in a cloud of probabilities until measurement collapses them into a single state. According to this view, reality is inherently probabilistic, and the wave function is not just a tool for calculation, but a description of what truly exists before observation. On the other hand, some interpretations, like the many worlds hypothesis, propose that the electron goes through both slits, but in different branches of reality. In this view, measurement does not collapse possibilities, but splits them, with each outcome realized in a parallel universe. Other physicists suggest hidden variables, unseen factors that determine the outcome behind the scenes, though experiments testing these ideas have consistently ruled them out. The unsettling truth remains. The double-slit experiment resists any explanation that preserves classical intuition. What makes the experiment so powerful is its simplicity. Anyone can understand its setup, and yet its results defy common sense. It does not require massive particle accelerators or exotic technology. It requires only a source of particles, a barrier with slits, and a detector screen. And still, it reveals a mystery that challenges our very definition of reality. Even more astonishing are the variations of the experiment. In some versions, scientists delay the decision to measure the path of the particle until after it has passed through the slits. The results suggest that the choice to observe retroactively determines whether the particle behaved as a wave or a particle. It is as though the present act of measurement reaches back in time, rewriting the past. This so-called delayed choice experiment blurs the boundary between cause and effect, suggesting that reality does not settle into a definite state until observation demands it, no matter when that demand occurs. For many, this is the first crack in the seemingly solid wall of reality. If particles behave differently depending on whether they are observed, then our universe is not independent of measurement. Reality is not simply out there, existing on its own terms. It is, in some sense, participatory, whether through consciousness, interaction, or some still unknown mechanism. The act of observing appears to weave the fabric of existence into a definite form. This experiment also raises unsettling philosophical questions. If reality depends on observation, then what was the state of the universe before life evolved? Did stars burn, planets form, and galaxies collide in indefinite states until awareness emerged to fix them in place? Or is there some deeper mechanism, beyond our comprehension, that serves as the universal observer? The double-slit experiment does not answer these questions. It only insists that they cannot be ignored. At its core, the double-slit experiment shows us that reality is not passive. It is dynamic, fluid, and somehow aware of the conditions under which it is being examined. That awareness might not be conscious in the human sense, but it is undeniable that the universe changes its behavior when measured. This is the crack in reality, the point where the solid picture of a stable, objective world begins to dissolve. Through those cracks, a stranger truth begins to shine, that existence is more delicate, more entangled with observation, and more mysterious than anyone expected. At the heart of quantum mechanics lies one of its most puzzling and controversial concepts: the observer effect. The double-slit experiment revealed that particles act differently when they are being measured, but it left open the question of what exactly constitutes a measurement. Is it the physical presence of a detector, the interaction of particles with a machine, or does the mind itself play a role in solidifying reality from a haze of probabilities? The observer effect challenges the comfortable idea that the universe is independent of us, existing with certainty whether we notice it or not. Instead, it suggests that reality is, at least in part, a co-production. Without observation, particles remain in a state of superposition spread across multiple possible outcomes. With observation, that ambiguity collapses into a definite result. This raises an almost unthinkable possibility that our act of looking, of noticing, is not passive but fundamental to the creation of the world we experience. To understand the roots of this paradox, consider the wave function, the mathematical description of all the possible states a quantum system can occupy. Before observation, an electron's wave function might describe it as existing in many places at once, or moving along several paths simultaneously. Yet the moment it is observed, the wave function appears to collapse, reducing the electron to a single, definite outcome. The mathematics works perfectly, but the mechanism is elusive. What exactly triggers this collapse? Some interpretations place the responsibility squarely on measurement itself. Any interaction with the environment, a detector, a photon bouncing off the particle, or even a subtle disturbance counts as observation and forces the system into a concrete state. This perspective avoids invoking consciousness directly, framing the collapse as a natural consequence of interaction. Yet even here the mystery persists. Why should a system of probabilities become definite only when something external intervenes? Why doesn't it remain a cloud of possibilities forever? Other physicists, more daringly, argue that consciousness itself is the key. This line of thought, though controversial, suggests that reality does not crystallize until it is registered by a conscious mind. In this interpretation, the universe waits to be observed, as though awareness is woven into the machinery of existence. This is not to say that human minds alone collapse the wave function, but that consciousness in general, whatever its true nature may be, plays a role in bringing probabilities into actuality. This idea has fascinated scientists, philosophers, and even mystics alike. If true, it means that the act of looking at the universe does not merely reveal what is already there, but participates in creating it. The observer and the observed are inseparable. The world is not an objective stage on which we play our roles, but a dynamic interplay between mind and matter. Reality, in this sense, becomes participatory, with observation acting as the bridge between the possible and the actual. But not everyone is comfortable with such an interpretation. Many physicists argue that bringing consciousness into the heart of quantum mechanics muddies the waters with philosophy and speculation. They prefer explanations that remain within the bounds of physics, attributing the collapse to decoherence. Decoherence describes how quantum systems interact with their surroundings, losing their fragile superposition states and appearing classical to our measurements. According to this view, the universe does not require consciousness to collapse wave functions. Environmental interactions do the job automatically, yet decoherence, while useful, does not fully resolve the paradox. It explains how superpositions become difficult to detect, but does not clarify why a specific outcome occurs rather than another. The unresolved tension between these perspectives has kept the observer effect at the center of debate for decades. On one side, the possibility that reality is fundamentally tied to awareness. On the other, the attempt to preserve a purely physical explanation without invoking the mind. Both approaches have strengths and weaknesses, and neither has been proven definitively correct. What makes the observer effect so profound is its implication for our relationship to the cosmos. If consciousness plays any role at all in shaping the universe, then we are not passive bystanders, but active participants. The boundary between mind and matter becomes blurred, and the very distinction between subject and object breaks down. This would mean that our perception is not just a window to reality, but a force that sculpts it. Even the cautious interpretations, which stop short of assigning agency to consciousness, still leave us with a radical picture. They tell us that reality is not fixed until it is engaged with. Possibilities hover in limbo until some interaction, some form of measurement, collapses them into facts. The everyday world, which feels so solid and independent, is revealed to be precarious, built on an invisible foundation of uncertainty that requires observation to resolve. The observer effect also sparks unsettling questions about the universe before observers existed. Did the cosmos exist in a vast state of probability before life arose? Were galaxies and stars definite entities long before consciousness appeared? Or were they smeared across possibilities until awareness emerged to pin them down? These questions are not easily dismissed, and they push us toward the realization that the very act of asking them places us within the puzzle we are trying to solve. Some thinkers have gone further, speculating that consciousness and the quantum world are deeply entangled, perhaps even two sides of the same coin. If that is the case, then understanding the observer effect may not only reshape our view of physics, but also illuminate the nature of the mind itself. The riddle of how observation shapes reality might be inseparable from the mystery of what consciousness is and why it exists at all. The paradox of the observer effect is that it cannot be avoided. Any attempt to probe the quantum world requires observation, and yet observation seems to change what we are studying. It is as though reality resists being fully revealed, shifting its form the moment we attempt to pin it down. This tension between what is possible and what becomes actual lies at the core of the quantum enigma. What remains clear is that the observer effect is not a trivial technicality. It is a profound statement about the nature of reality and our role within it. Whether the ultimate explanation lies in consciousness, in interactions, or in some future theory we cannot yet imagine, the observer effect forces us to confront the possibility that the universe is not entirely independent of our participation. It insists that we rethink what it means to know, to measure, and to exist. The double-slit experiment opened the first crack in reality, but it is the observer effect that widens it into a chasm. Through it, we glimpse a world where certainty dissolves, where probabilities reign, and where observation itself plays a role in conjuring the universe into form. Few images capture the disturbing strangeness of quantum mechanics more vividly than the thought experiment of Schrödinger's cat. At first glance, it sounds absurd, even comical, but it was designed as a serious critique of how far the implications of quantum theory stretch when taken literally. Beneath the humor lies a brutal paradox. Can something be alive and dead at the same time? And if so, what does that mean for the existence of reality before it is observed? In 1935, Erwin Schrödinger, one of the founding architects of quantum mechanics, posed his famous scenario. Imagine a cat sealed inside a box. Inside this box is a tiny vial of poison, a Geiger counter, and a single atom that has a 50% chance of decaying within a given time. If the atom decays, the Geiger counter detects it, triggers the release of the poison, and the cat dies. If the atom does not decay, the poison remains sealed, and the cat lives. The cruel twist is this. According to quantum mechanics, until the box is opened, the atom exists in a superposition of decayed and not decayed. By extension, the cat, entangled with the atom state, is both dead and alive simultaneously. To Schrödinger, this was not a playful riddle, but a sharp critique. He was highlighting the absurdity of applying quantum principles to the everyday world. How could a cat possibly be both alive and dead? He intended it to expose the inadequacy of interpreting the wave function as a literal description of reality. Yet instead of dismissing the paradox, the physics community found itself unable to escape it. The logic of quantum mechanics, bizarre though it may be, forces us to grapple with the possibility that until observation occurs, the cat is indeed suspended between contradictory states. This is not a paradox we can brush aside with clever wording. The cat is not alive in one sense and dead in another. The mathematics suggests it is both simultaneously, with its reality unresolved until observation collapses the superposition into one outcome. What does it mean for something as concrete as life and death to hang in limbo? That is the question Schrödinger wanted to force upon the world. The thought experiment shines a light on the deep tension between the quantum and classical realms. On the quantum scale, particles routinely exist in multiple states at once. Electrons orbit nuclei in clouds of probability. Photons travel paths that overlap and interfere. Atoms remain undecided between energy levels, but when scaled up into the world we see, these ambiguities disappear. Cats are either alive or dead. Boxes contain one reality or another, never both. So where exactly is the boundary? At what point does the blurry superposition of the quantum world sharpen into the clarity of everyday reality? This unresolved question is known as the measurement problem, and Schrödinger's cat is its most haunting embodiment. The paradox lays bare the inadequacy of current explanations. If observation is what collapses superposition, then until someone opens the box, the cat's fate is suspended. But what if the box is opened by a machine instead of a conscious mind? What if the cat itself is an observer, aware of its own state inside the sealed chamber? The problem multiplies rather than resolves. Some interpretations of quantum mechanics attempt to sidestep the paradox altogether. The Copenhagen interpretation insists that the wave function is merely a tool for calculating probabilities, not a literal description of reality. According to this view, the cat is not really both alive and dead. It is only our knowledge that is incomplete until the box is opened. Yet this interpretation, while pragmatic, does not sit comfortably with many. If the wave function is not real, then what exactly governs the behavior of particles before we look? Other interpretations lean into the paradox rather than avoiding it. The many worlds interpretation argues that the cat is both alive and dead, but in different branches of reality. When the box is opened, the universe splits, creating one world where the cat lives and another where it dies. There is no collapse of the wave function, only a branching of possibilities into separate realities. While this solves the problem in one sense, it introduces an even wilder vision of existence, an endless proliferation of parallel worlds, each containing different versions of events. Still others turn to decoherence, the idea that superpositions unravel, not because of observation itself, but because of entanglement with the environment. In this view, the cat is not in a mystical limbo, but entangled with countless particles in its surroundings, which quickly wash out the observable effects of superposition. Yet decoherence, while useful for explaining why quantum effects fade in large systems, does not eliminate the paradox entirely. It tells us why we do not see cats in superpositions, but not why a definite outcome occurs instead of another. The paradox of Schrödinger's cat is unsettling precisely because it refuses to be dismissed. It forces us to confront the possibility that reality is not as definite as we assume. Before observation, the world might exist as overlapping possibilities, unresolved and contradictory. If so, then the solid world we perceive is not a fundamental given, but a fragile construct, emerging only through the act of measurement or awareness. The implications stretch far beyond physics. If life and death themselves can be suspended in superposition, then the boundary between possibility and actuality is more porous than we ever imagined. Schrödinger's cat may be a thought experiment, but it illuminates a truth that cannot be confined to a sealed box. The paradox extends into every corner of the quantum world, whispering that reality itself may not exist in definite form until it is forced to. This is why Schrödinger's cat continues to haunt discussions of quantum mechanics. It is not merely a metaphor or a joke. It is a mirror held up to the logical impossibilities at the core of modern physics. It compels us to ask whether the world exists independently of us, or whether it requires our observation to become real. It challenges us to consider that the impossible, the coexistence of life and death, of contradictory states, may not only be possible, but fundamental. Among the many peculiarities of quantum mechanics, none unsettled Albert Einstein more than the phenomenon known as entanglement. To him, it seemed like the very embodiment of what he once mocked as spooky action at a distance. It defied the foundations of classical physics, threatened to undermine the principle of locality, and suggested that particles separated by vast stretches of space could remain connected in ways that transcended time and distance. What was meant to be a quirk of the mathematics soon became one of the most profound revelations about the hidden fabric of the universe. Entanglement occurs when two particles interact in such a way that their properties become correlated, no matter how far apart they are later separated. Imagine creating a pair of electrons with opposite spins. Once entangled, measuring the spin of one electron immediately tells you the spin of the other, even if the two are on opposite sides of the galaxy. This would not be particularly shocking if the electrons carried fixed properties with them from the start, but quantum mechanics insists that until measured, their states are undefined, existing in superposition. The moment one is measured, the other collapses into a complementary state, faster than any signal could travel between them. Einstein could not accept this. He believed that quantum mechanics, while effective, was incomplete. In 1935, along with Boris Podolsky and Nathan Rosen, he formulated what became known as the EPR paradox. The argument was straightforward. If quantum mechanics were correct, then entangled particles would have to communicate instantaneously across space. This would violate relativity, which dictates that nothing can travel faster than light. Therefore, Einstein reasoned, there must be hidden variables, unknown factors embedded in the particles that determine their properties in advance. Quantum mechanics, he argued, was only a partial description of reality. For decades, the EPR paradox stood as one of the most serious challenges to quantum theory. It highlighted a contradiction between the probabilistic world of quantum mechanics and the deterministic, local world of relativity. To preserve sanity, many physicists quietly assumed that hidden variables must exist, even if they could not yet be identified. After all, the alternative was too outrageous. A universe where particles remained linked across infinite distances, transcending the limits of space and time. But in the 1960s, a physicist named John Bell devised a way to test the issue experimentally. Bell's theorem showed that if hidden variables govern the behavior of particles, then certain statistical correlations would be limited. If quantum mechanics were correct, however, entangled particles would violate those limits. The predictions could be tested in the laboratory, and the results would speak for themselves. Beginning in the 1970s and continuing into the modern era, experiment after experiment confirmed what Einstein had hoped was impossible. Quantum mechanics was right. Entangled particles behaved exactly as the theory predicted, producing correlations that could not be explained by any local hidden variables. The eerie conclusion was unavoidable. Entanglement is real, and the universe permits connections that defy classical intuition. What makes entanglement so radical is not simply the speed at which information seems to travel, but the suggestion that information does not travel at all. Instead, it is as though the entangled particles are not separate entities, but part of a single, unified system. No matter how far apart they may be, their identity is shared, and measurement of one instantly resolves the state of the other, not by sending a signal, but by revealing what was already tied together at the most fundamental level. This insight opens a new way of viewing the cosmos. Rather than a collection of independent objects scattered through space, the universe may be a vast web of entangled connections where separation is an illusion. What happens in one location can be inseparably linked to events in another, across any distance. Reality, in this view, is not local, but holistic, woven together by invisible threads that transcend the limits of time and space. The implications stretch into technology as well as philosophy. Entanglement has become the cornerstone of emerging fields, like quantum computing and quantum cryptography. By exploiting the correlations of entangled particles, scientists hope to build machines that perform calculations beyond the reach of classical computers, or create communication systems that are unbreakable by any known means. These practical applications remind us that entanglement is not just a curiosity, but a real phenomenon with measurable power. Yet beyond the laboratories, the philosophical shock remains. Entanglement suggests that our ordinary view of reality of distinct objects existing separately, governed by local rules, is incomplete. The deeper truth is that everything may be connected, not metaphorically, but literally. In the strange language of quantum mechanics, the universe does not respect our classical boundaries. It whispers of a reality where distance does not diminish connection, and where the fabric of existence is stitched together by bonds we cannot see. For Einstein, this was unacceptable. He wanted a world governed by certainty, locality, and order. For Bohr and those who embraced quantum mechanics, it was simply a new kind of order, one that defied the old assumptions, but revealed deeper truths. The clash between these visions continues to shape debates about the nature of reality, forcing us to grapple with a universe that behaves less like a machine and more like a seamless, interconnected whole. Entanglement is more than an abstract concept. It is a paradox that challenges the very structure of existence. If two particles can remain united across the breadth of the cosmos, then perhaps nothing is truly separate. Perhaps the universe itself is one vast entangled state, with every part reflecting the whole. That possibility forces us to reconsider what it means to exist, to act, and to know. It suggests that beneath the surface of separateness lies a deeper unity, one that binds the cosmos together in ways both profound and incomprehensible. Of all the unsettling consequences that emerge from the study of quantum mechanics, none is more disorienting than the challenge it poses to causality itself. In our everyday experience, time flows in one direction. Causes lead to effects. The past determines the present, and the present shapes the future. This linear order seems so natural that we rarely question it, yet experiments in the quantum realm have hinted at something almost unthinkable: the possibility that the future can reach back to influence the past, rewriting our most basic understanding of cause and effect. The seeds of this paradox were planted in the very experiments we have already encountered. The double-slit setup, when modified, has given rise to what are called delayed choice experiments. These experiments were proposed in the 1970s by physicist John Archibald Wheeler, who asked a startling question. What if the decision to observe a particle is delayed until after the particle has already passed through the slits? Common sense would suggest that the particle's behavior should be fixed by that point, yet quantum mechanics predicts otherwise, and the experiments have borne it out. In a delayed choice experiment, the decision of whether to measure the particle's path is made only after it should have already chosen its trajectory. If the detectors are in place, the particle behaves like a particle, as if it had gone through one slit. If they are absent, the particle behaves like a wave, as if it had gone through both. But here is the puzzle. How could the particle have known whether the detectors would be present if that decision had not been made yet? It is as though the future act of measurement reaches back in time, determining the particle's earlier behavior retroactively. Even more dramatic are the so-called delayed choice quantum eraser experiments. In these setups, particles are entangled, and the decision to preserve or erase the information about their path can be made after they have already hit the detector screen. Astonishingly, whether an interference pattern appears depends not on what happened in the past, but on the choice made in the future. In other words, the results recorded earlier in time are shaped by a decision that occurs later. These experiments do not allow us to send messages backward in time or alter history in the science fiction sense, but they force us to confront the possibility that our intuitive notion of temporal order does not hold at the quantum level. The future and the past are not strictly separated. Instead, they appear to be woven together in ways that allow influences to flow in both directions. What does this mean for our understanding of reality? One interpretation is that causality itself is not fundamental but emergent. At the quantum level, events are not bound by the arrow of time as we experience it. Instead, they form a web of correlations that transcend linear order. The universe does not progress neatly from past to present to future, but exists as a whole, with connections that defy temporal sequence. In this view, time is less like a river and more like a tapestry, where every thread is woven in relation to the others, regardless of direction. Another possibility is that our notion of cause and effect is an illusion imposed by the macroscopic world. On the quantum scale, what we call causes and effects are simply correlated outcomes of an underlying reality that does not respect temporal order. The future does not literally change the past, but both are linked through a deeper structure that transcends time. In this sense, the apparent retrocausality is a window into the inadequacy of our classical categories, not a violation of logic. Still, the philosophical implications are staggering. If the future can shape the past, then our picture of reality as a chain of determinate events collapses. Instead of a universe driven forward by causal necessity, we are confronted with a universe where past, present, and future are entangled in a timeless whole. Our role as observers takes on new significance, for the choices we make now may not only influence what happens next, but also what has already happened at the quantum level. This perspective has not gone unnoticed outside of physics. Philosophers and theologians have seized on retrocausality as evidence that time may be far less absolute than we assume. Mystics have long spoken of the unity of past, present, and future, and the quantum experiments give this intuition a startling scientific resonance. The rigid walls between what has been and what will be begin to crumble, replaced by a vision of reality in which every moment participates in shaping every other. Skeptics argue, of course, that these interpretations go too far. They caution that the mathematics of quantum mechanics, while strange, does not necessarily imply time travel or retroactive causation in the literal sense. Instead, they see the results as reflections of correlations established at the moment of entanglement, with no need for the future to reach backward. Yet even these cautious explanations cannot erase the unease. The experiments do not fit comfortably within the classical framework, and the door to deeper mysteries remains open. Ultimately, the causality question exposes one of the deepest fractures in our understanding of the universe. If time is not what it seems, then our most basic assumptions about existence must be reconsidered. Are we moving through time? Or is time an illusion created by our perception of change? Do we influence the past simply by making choices in the present? Or is the entire span of reality fixed, with our experience of causality no more than a limited perspective on a timeless whole? Quantum mechanics does not resolve these questions, but it forces us to confront them. The experiments that hint at retrocausality are not obscure curiosities. They are rigorous, repeatable, and undeniable. They tell us that the universe is stranger than the linear order we impose on it, that the boundaries between before and after are not as solid as we think. They whisper of a reality in which time itself may be malleable, where the future and the past are intertwined in ways our minds can barely begin to grasp. Few concepts in quantum theory unsettle the human imagination more than superposition. At its core, it suggests that a single particle can exist in multiple states simultaneously until an act of measurement forces it into a definite outcome. For those raised in the world of classical physics, where objects occupy clear positions and follow predictable paths, this idea sounds almost absurd. And yet, it is not speculation. It is the very fabric of quantum mechanics, confirmed by experiments and calculations repeated countless times over the last century. Superposition emerges from the wave-like behavior of particles. In quantum mechanics, the state of a particle is described by a mathematical object known as the wave function. This wave function does not pinpoint where the particle is or what state it occupies. Instead, it encodes probabilities for every possible outcome. Before measurement, the particle is not in one state or another. It exists in all of them at once, a blend of possibilities that only becomes definite when observed. Consider an electron, a particle so tiny that quantum effects dominate its behavior. Left unmeasured, the electron can be in multiple locations at the same time. Its wave function stretches across space, assigning a probability to every potential spot it might appear. When we detect it, the wave function seems to collapse, and the electron is found in one place. But until that moment, it is not correct to say it was really in one position or another. It was in a superposition of them all. This is not just a mathematical trick. Superposition has been demonstrated in experiments with photons, electrons, and even molecules composed of thousands of atoms. In each case, the systems behave as though they are in multiple states simultaneously, until a measurement reduces them to a single outcome. The fact that larger and more complex systems can exhibit superposition raises an unsettling question. If molecules can do this, where does it stop? Could entire macroscopic systems or even ourselves exist in superposition? The idea of superposition becomes even more provocative when extended to thought experiments like Schrödinger's cat. In this scenario, a cat inside a sealed box is linked to a quantum event that has a 50% chance of releasing poison. If the quantum system is in a superposition of triggered and not triggered, then the cat is likewise in a superposition of alive and dead until someone opens the box. The thought experiment was intended to highlight the absurdity of applying quantum logic to everyday objects, yet it reveals the heart of the paradox. If quantum mechanics applies universally, then reality itself may consist of countless overlapping possibilities that only appear definite from the perspective of an observer. This leads naturally to one of the boldest interpretations of quantum mechanics, the many worlds hypothesis, proposed by Hugh Everett in the 1950s. This view rejects the collapse of the wave function. Instead, it argues that all possible outcomes of a quantum event are realized, but in separate branches of reality. In one branch, the electron appears here. In another, it appears there. In one world, Schrödinger's cat is alive. In another, it is dead. Every act of measurement does not eliminate possibilities, but instead splits the universe into parallel realities, each equally real. The implications of this interpretation are staggering. If true, it means that our universe is just one of an unfathomable number, endlessly branching at every quantum decision point. Every time we flip a coin, make a choice, or even breathe, the quantum states of countless particles divide reality into alternate versions. Somewhere in another branch, every possibility you can imagine is playing out. Skeptics often dismiss the many worlds interpretation as extravagant. Why multiply universes beyond necessity, they ask, when the simpler idea of wave function collapse suffices? Yet the many worlds view has one advantage. It avoids the problem of retrocausality and the observer effect. In Everett's picture, there is no need for consciousness to collapse the wave function or for the future to reach into the past. Instead, all outcomes coexist, and we simply find ourselves in the branch where one particular result occurred. Still, even if we set aside the many worlds hypothesis, the phenomenon of superposition remains. It challenges our assumptions about identity, existence, and reality itself. If a particle can be in multiple states at once, what does it mean to say that it is anything at all? Perhaps what we call reality is not made of definite objects, but of overlapping waves of probability that only crystallize into certainty when observed. Experiments continue to push the boundaries of superposition. Physicists are working to place larger and larger systems into such states, testing the limits of quantum mechanics. If an object visible to the naked eye could be shown to exist in a superposition, it would erase any lingering doubt that this phenomenon is more than a mathematical abstraction. It would force us to confront the possibility that our macroscopic world of solidity and certainty is built on a foundation of overlapping realities that remain hidden from view. What superposition reveals is that reality is not singular, but layered. Beneath the surface of our everyday experience lies a domain where the very notion of either-or gives way to both-and. A photon is both wave and particle. An electron is both here and there. A cat is both alive and dead. And in that ambiguity lies the possibility that our universe is one of countless others, each equally valid, each equally real, each born from the strange logic of quantum mechanics. Among the interpretations of quantum mechanics, none has ignited the imagination more profoundly than the many worlds hypothesis. Born from Hugh Everett's bold rethinking of quantum theory in the mid-20th century, it presents a vision of reality that is simultaneously elegant and unsettling. Instead of relying on the mysterious collapse of the wave function, Everett argued that quantum superpositions never vanish. All outcomes of every quantum event occur, but each in its own branch of the universe. At first glance, this idea appears excessive. Why create endless universes just to account for a few probabilities? Yet the elegance lies in its consistency. If quantum mechanics is to be taken literally, without inserting hidden collapses or consciousness-driven reductions, then superpositions must remain intact. Measurement does not eliminate possibilities. It separates them. Each branch contains a full version of reality, complete with observers, histories, and futures. Imagine a simple coin toss. In the classical world, the coin lands heads or tails, and that outcome becomes fixed. In the quantum realm, however, the many worlds view says that both outcomes happen. One universe sees the coin fall heads, while another, just as real, sees tails. To the observer in each branch, it appears as though a single result occurred. Yet from the grand perspective of the multiverse, both persist in parallel. This branching does not only occur in laboratory setups or trivial coin flips. Every quantum event contributes to the proliferation of universes. Every photon reflecting from your skin, every electron shifting in your brain, every atom vibrating in the air adds to the division. The sheer scale of branching defies comprehension. Within a single moment, an inconceivable number of universes could be generated, each carrying its own timeline forward. The unsettling implication is that there are versions of you who have lived out every possible choice you could have made. In one branch, you chose to stay home. In another, you took a risk and changed your life. In countless others, subtle differences accumulated into entirely different destinies. According to many worlds, none of these versions is more or less real than the one you inhabit now. They all exist, woven into the expanding fabric of the multiverse. This picture of branching universes raises profound questions about identity and meaning. If every possible version of your life is lived somewhere, what does it mean to say that you made a choice? The very notion of free will seems to dissolve. For you, in this branch, your decisions feel absolute. But in the broader multiverse, every decision is taken, and every consequence unfolds. Choice may be less about creating one future, and more about locating yourself in one among countless others. Scientists and philosophers debate whether this interpretation adds explanatory power or simply multiplies complexity. Yet many worlds has advantages over rival interpretations. It avoids the need for a special observer effect, sparing us the paradox of consciousness collapsing wave functions. It preserves the mathematical purity of quantum mechanics without adding arbitrary rules. And it offers an answer to why quantum events appear random. Randomness is simply the experience of finding ourselves in one branch rather than another. Still, the many worlds hypothesis is not without its difficulties. Chief among them is testability. How can we confirm the existence of branches we cannot interact with? Each universe evolves independently, sealed off from communication with the others. To critics, this makes the theory unfalsifiable, little more than speculative metaphysics. To supporters, however, its strength lies not in direct evidence, but in logical coherence. By following the equations of quantum mechanics wherever they lead, we arrive at a multiverse whether we like it or not. In recent years, many worlds has gained traction in discussions of cosmology and information theory. The vastness of branching universes dovetails with the possibility of parallel worlds predicted by inflationary cosmology. Some researchers even suggest that quantum computing works by exploiting interference among branches, though this claim remains controversial. Regardless of the details, the idea has seeped into the cultural imagination, inspiring stories, films, and countless philosophical debates. The paradox at the heart of many worlds lies in its challenge to our concept of reality. If every possibility is realized, then the universe we experience is only a fraction of what exists. Reality becomes not a singular path, but an infinite tree, branching endlessly with every quantum event. This defies our instinctive need for certainty, for a world that is consistent and knowable. Instead, it paints a picture of a cosmos where every possibility, no matter how improbable, is given space to exist. The question that lingers is whether this vision enhances or diminishes our sense of meaning. Some find comfort in the idea that no possibility is lost, that every version of life is lived. Others feel unsettled, as if their choices are robbed of significance in a sea of infinite alternatives. Yet perhaps the paradox is not meant to comfort or unsettle, but to expand our horizon. By considering that every outcome may exist, we are forced to reconsider what reality is and what it means to inhabit just one path among the many. Whether or not many worlds is the ultimate description of reality, it represents one of the most daring attempts to grapple with the strangeness of quantum mechanics. It asks us to accept that the universe may be far larger, stranger, and more fragmented than our senses suggest. It offers a paradox that by clinging to the straightforward mathematics of quantum theory, we arrive at a vision of reality that stretches the imagination to its breaking point. Few extensions of the many worlds hypothesis strike as deeply at human existence as the notion of quantum immortality. Unlike the abstractions of wave functions or the puzzles of entanglement, This idea speaks directly to the question every human being wrestles with. What happens when we die? At its heart, quantum immortality is a thought experiment, but it is one that builds directly on the branching logic of the multiverse. If every possible outcome of a quantum event is realized in some universe, then in principle, there is always at least one branch where an observer survives, no matter how dire the circumstances. To understand this, imagine a dangerous experiment, one with a 50% chance of ending in instant death and a 50% chance of survival. In a classical world, you flip the coin of fate and either live or die. But in the many worlds framework, both outcomes occur. In one branch, the observer perishes. In another, they continue unharmed. For those outside the experiment, both versions exist in separate realities. But for the observer, the story is stranger. From the inside, consciousness can only persist in the branch where survival occurs. Death, by definition, cannot be experienced. Therefore, subjectively, the observer always finds themselves alive, no matter how improbable the survival outcome may be. This is the essence of quantum immortality. The idea that consciousness, tied to the survival of an observer, might never encounter an endpoint. Even as universes branch and most versions perish, the self continues in the threads where life endures. It paints a picture of reality where death is not an experienced event, but a divergence into branches inaccessible to the continuing self. On the surface, this sounds like a bizarre promise of eternal life. If true, it would suggest that each of us will always experience survival from our own perspective, no matter how catastrophic the odds. But the unsettling part is not just survival, it is the conditions under which it happens. Quantum immortality does not guarantee comfort or well-being. It merely ensures continuity. That means the surviving self might find itself in increasingly improbable circumstances, living through disasters, defying accidents, or existing in worlds that feel distorted and fragile. This brings us to the deeper paradox. If consciousness is tied to survival in branching universes, then the end of life may never truly arrive from the first-person point of view. But this survival is not the kind imagined in religions or myths of eternal peace. It is a raw, almost mechanical continuation, where improbability is overcome simply because there must be some branch in which it happens. Such survival could, in principle, stretch endlessly forward, carrying the observer into futures that grow stranger and more improbable with each escape. The implications are difficult to reconcile with our everyday experience of mortality. We see others die. We know that biological systems break down. Death appears final and absolute. Yet quantum immortality forces us to consider the possibility that the experience of death belongs to the external observer, not the subject. From within, the subject might never pass into non-existence. Instead, their awareness flows along the thin threads of survival, always finding the branch where continuity is preserved. Philosophers and physicists have debated whether this idea can be taken seriously, or whether it is simply an illusion created by pushing many worlds too far. Some argue that it mistakes probability for inevitability, that survival in unlikely branches does not mean eternal survival. Others suggest that consciousness might not follow quantum branching so neatly, that it may be tied to physical structures in ways that do not allow such continuity. Yet the thought experiment remains compelling because it refuses to let go of a simple truth. You cannot experience not being. If consciousness truly does persist only in branches where it endures, then immortality may be less a gift than a burden. Imagine the passage of centuries, then millennia. As the body weakens, but improbable survival continues. Imagine persisting into a world where everything else has changed, where civilization collapses or stars burn out, yet some version of you remains. Quantum immortality forces us to confront not just the end of life, but the possibility of its endless extension. Stripped of the comforts of meaning or design, This perspective does not replace the biological reality of death as we know it. For those around us, mortality is absolute. Lives end, bodies fail, histories close. But at the edge of quantum logic, there lingers the possibility that consciousness itself cannot be extinguished from within. The paradox is not just that we might never experience death, but that we might be trapped in survival, carried along the thinnest threads of existence long after all likelihood of life has passed. For some, this idea sparks hope, the dream of a self that never fades. For others, it is terrifying, a vision of existence stretched beyond its natural bounds, survival without resolution. Either way, quantum immortality exposes the limits of our understanding of consciousness and forces us to ask whether death is truly as final as it seems. What makes this thought experiment so powerful is not its certainty, but its challenge. It asks us to rethink what it means to live, to die, and to exist in a universe where probabilities never vanish. It is a reminder that quantum mechanics does not simply describe particles in laboratories. It cuts into the heart of what it means to be, raising questions no human has ever fully answered. When we strip physics down to its bones, a surprising pattern emerges. Beneath particles, beneath forces, beneath even the fabric of space and time, there may be something more fundamental. Information. Not information in the casual sense of words or numbers, but quantum information. The raw binary of existence encoded in quantum bits. This shift in perspective reframes the universe not as a stage of matter and energy, but as a cosmic computation, where everything we see, touch, and experience is an emergent product of underlying informational rules. To understand this, it helps to compare with ordinary computing. Classical computers process information in bits, zeros, and ones that switch between definite states. Quantum systems, however, operate on qubits. A qubit is strange because it can exist in a blend of states, a superposition of 0 and 1 until measured. This means that quantum information is not rigid but fluid, capable of carrying vast amounts of possibility in a single unit. If the world is built on such qubits, then the universe itself may be structured like an immense quantum processor. This perspective is not mere metaphor. Quantum information theory has shown that particles, fields, and even black holes obey principles best described in terms of information rather than material substance. For example, entanglement, once considered spooky and inexplicable, can be understood as a correlation of quantum information shared across space. What looks like action at a distance is in fact the consistency of information woven into the structure of reality. Likewise, quantum teleportation, the transfer of a quantum state from one location to another, works not by moving particles, but by transmitting information that reconstructs the original state elsewhere. Some physicists argue that space itself emerges from networks of quantum information. Entanglement patterns, when mapped, can give rise to the geometry of spacetime. In this view, distance is not fundamental, but arises from how information is entangled across the fabric of reality. This idea suggests that what we call the physical universe may be nothing more than the manifestation of quantum informational relationships, much like a digital world emerges from lines of code. Black holes provide one of the most striking arenas for this perspective. For decades, scientists debated whether information swallowed by a black hole was destroyed forever. Stephen Hawking famously argued that it was lost, creating a paradox because the laws of quantum mechanics insist that information cannot be erased. Later work, however, suggested that information is not destroyed, but scrambled across the black hole's surface, encoded in a thin boundary known as the event horizon. This led to the holographic principle, the radical notion that everything inside a region of space could be fully described by information written on its boundary. It is as if the universe itself is a hologram, with three-dimensional reality arising from two-dimensional informational structures. This view transforms physics into something resembling computer science. The laws of motion, thermodynamics, and quantum mechanics may be emergent rules in the grand calculation. What we perceive as matter may be compressed information. What we call energy may be the transformation of code. Even the constants of nature could be programming parameters. Instead of asking what the universe is made of, we begin to ask what rules govern the processing of information that gives rise to the universe. The implications stretch far beyond physics. If reality is built from quantum information, then consciousness itself may be understood as an informational process running on the hardware of the brain, tied to the deeper informational substrate of the cosmos. Identity, memory, and perception might not be isolated biological accidents, but emergent phenomena in a universe designed to compute. This does not reduce existence to something mechanical. Instead, it elevates information to the most profound level, making it the very essence of being. Skeptics caution against pushing the metaphor too far. Just because the universe can be described in terms of information does not mean it literally operates like a computer. Yet the predictive power of quantum information theory is undeniable. It has already revolutionized technology, giving rise to quantum cryptography and quantum computing, tools that harness the peculiar rules of qubits to solve problems intractable to classical machines. These breakthroughs are not symbolic. They prove that quantum information is not an abstraction, but a real and manipulable aspect of the world. If the universe is code, the question arises, who or what is running it? Some interpret the idea in almost theological terms, imagining a cosmic programmer or simulation. Others prefer to see it as a self-contained system, running without external input, an eternal engine of information unfolding according to its own internal logic. Either way, the informational view forces us to rethink the nature of existence. Reality may not be a solid, objective stage, but a dynamic, computational process, constantly evolving as qubits shift and entangle. This perspective ties back into the deepest mysteries. Why is the universe comprehensible to mathematics? Because mathematics may be the language of the code itself. Why does quantum mechanics resist classical intuition? Because we are peering directly into the logic of information rather than matter. Why does space-time bend and stretch under gravity? Because geometry might be an emergent property of entangled information networks. Each of these puzzles begins to make sense if information is primary. The startling conclusion is that everything from the motion of galaxies to the spark of thought in your mind can be traced back to the same substrate of quantum information. Existence itself is computation, not symbolic, not metaphorical, but real. If this is true, then the universe is not a static object, but a living process, a constant unfolding of informational interactions, vast beyond comprehension, yet bound by simple rules that echo the ones we use to build our own machines. Among the strangest arenas of physics lies the black hole, an object so dense that space and time collapse into a singular boundary where nothing escapes. For centuries, black holes were thought of as simple cosmic vacuums, swallowing matter and light without return. But when quantum mechanics was applied to these monsters, a riddle emerged that shook the foundation of science: the information paradox. This paradox, raised most famously by Stephen Hawking, forced physicists to confront whether the fundamental laws of the universe are consistent, or whether reality itself breaks under the weight of black holes. To understand the paradox, we begin with how black holes form. When a massive star burns out its fuel, gravity overwhelms its structure, pulling matter inward until it collapses to an infinitely dense point called a singularity. Around this singularity forms the event horizon, the surface beyond which escape is impossible. Classical physics insists that whatever crosses this boundary is gone forever. Information about its shape, composition, or history ceases to matter. For decades, that seemed acceptable, until quantum mechanics reminded us that information cannot simply vanish. Quantum theory has a strict rule. The evolution of a system is unitary, meaning the information about its initial state is always preserved, even if it becomes scrambled. Information can change form, but it cannot be erased. This principle is so central that losing it would undermine the reliability of physics itself. Yet Hawking's groundbreaking work in the 1970s appeared to show that black holes defy this rule. Hawking discovered that black holes are not perfectly black. Through quantum effects near the event horizon, particles and antiparticles can spontaneously appear. One falls in, the other escapes, creating what is now called Hawking radiation. Over time, this process causes the black hole to evaporate. If it fully evaporates, then all matter that fell inside is gone, along with every detail of its information. What remains is thermal radiation, which carries no record of the original state. This outcome directly contradicts the unitarity of quantum mechanics, giving rise to the information paradox. This problem is not a technicality, it is a clash of principles. Either quantum mechanics is incomplete, or general relativity is. If information is lost, the foundation of physics crumbles. If it is preserved, we must radically rethink what black holes are. This tension has inspired decades of research, with some of the most brilliant minds attempting to resolve it. One leading idea is that information is not destroyed but encoded on the surface of the black hole, smeared across the event horizon in microscopic patterns. This interpretation aligns with the holographic principle, which suggests that a three-dimensional region of space can be described by data stored on its two-dimensional boundary. In this picture, when matter falls in, the information about it does not vanish, but is written into a kind of cosmic ledger on the event horizon. Hawking radiation then may carry traces of this information back into the universe in highly scrambled form. Another approach, known as black hole complementarity, proposes that information is both reflected at the event horizon and passes inside depending on the observer's perspective. For someone falling into the black hole, reality unfolds normally until they are crushed at the singularity. For an outside observer, nothing ever truly crosses the horizon. Instead, the information is gradually re-emitted through radiation. These two accounts cannot be compared because no observer can experience both perspectives, meaning the contradiction never manifests in measurable ways. Yet even these solutions raise new challenges. Recent debates have centered on the firewall paradox, which questions whether the event horizon is smooth, or if it burns with destructive energy that destroys any infalling observer. The firewall proposal tries to resolve contradictions by breaking the equivalence principle of general relativity, which says falling into a black hole should feel uneventful at first. If firewalls exist, they would violate our most trusted description of space-time. If they do not, then we are back to facing the original paradox. What makes the information paradox so powerful is its reach. It does not only concern black holes, it concerns the consistency of physics itself. If information is not preserved, then the universe loses its predictability. Laws of nature would become statistical accidents, and causality would collapse. Conversely, if information is preserved, then we must accept that reality is structured in ways far stranger than classical intuition allows, with information flowing across surfaces and radiation carrying encrypted histories of everything ever consumed by a black hole. Some theorists suggest that the paradox hints at a deeper theory that unifies quantum mechanics and gravity. String theory and quantum gravity research often use black holes as testing grounds for such unification. In certain string theory models, black holes are described not as mysterious voids, but as highly complex configurations of fundamental strings and branes. In these models, information is always preserved, just distributed in unfamiliar forms. At its heart, the information paradox challenges how we conceive of reality. It asks whether destruction is ever truly final, or whether every event, no matter how violent, leaves a trace written into the cosmic ledger. If information survives even in the most extreme conditions, then perhaps nothing in existence is ever truly lost. This idea resonates with the broader theme of quantum physics. Where possibilities linger, superpositions exist, and entanglement stretches across the universe. Black holes, instead of being cosmic erasers, may be the ultimate archivists, holding secrets of everything they devour. And yet, the paradox remains unresolved. New experiments may never reach inside a black hole, but theoretical progress continues to push the boundaries of what we know. Each attempt at resolution suggests that black holes are not just astrophysical curiosities, but keys to the deepest workings of reality. They are mirrors reflecting the limits of our understanding and perhaps pointing toward the code that underlies the cosmos itself. The universe feels permanent. Galaxies sweep across the cosmos for billions of years. Stars burn with unimaginable persistence, and even the empty void between them seems unchanging. Yet modern quantum physics presents a terrifying possibility. The very fabric of reality may be unstable. What we call empty space might not be the lowest possible state of the vacuum, but rather a precarious balance perched on the edge of collapse. If this fragile balance were to give way, a single quantum fluctuation could trigger a chain reaction that rewrites physics everywhere, erasing our universe in an instant. To grasp this idea, we must first understand what physicists mean by vacuum. In ordinary language, a vacuum is simply the absence of matter. But in quantum field theory, the vacuum is far more than emptiness. It is a seething stage filled with fluctuating fields and virtual particles that briefly appear and vanish. These quantum fluctuations are not noise layered onto emptiness. They are the structure of space itself. From this restless background arise all the forces, particles, and interactions that shape the cosmos. But what if this vacuum is not the most stable configuration? The laws of physics allow for the possibility that what we call our vacuum is actually metastable. In other words, it sits in a false minimum, like a ball balanced in a shallow valley that is not the deepest one. The ball may remain there for billions of years, but it is not secure. A large enough disturbance or even a quantum fluctuation could nudge it into rolling toward the true minimum. If that deeper valley exists, the entire universe would transition into it. This transition is what physicists call vacuum decay. If our vacuum is indeed metastable, a bubble of true vacuum could spontaneously form somewhere in the cosmos. Once born, this bubble would expand at nearly the speed of light, devouring everything in its path. Within the bubble, the laws of physics themselves would be rewritten. Particles as we know them would dissolve, atoms would disintegrate, and chemistry would collapse. No observer would ever see the bubble arrive, because the transformation would be instantaneous and final. From the inside, there would be no survivors, only a new universe operating under different rules. The chilling aspect of this possibility is that it is not pure speculation. Calculations based on the Higgs field, the field responsible for giving particles their mass, suggest our universe might indeed be metastable. Measurements of the Higgs boson mass, combined with the top quark mass, place the vacuum precariously near the boundary between stability and instability. In simple terms, the numbers we have observed imply that our universe could be balanced on a knife's edge. It has persisted for over 13 billion years, but nothing guarantees it will persist forever. This idea transforms the concept of permanence. What we see as unshakable cosmic architecture, galaxies, black holes, stars, could all be swept away in a single event that no one could predict or stop. Vacuum instability does not operate on a timetable. It could occur a trillion years from now, or it could have already begun somewhere beyond our cosmic horizon, rushing toward us invisibly. Because the bubble moves at light speed, there would be no warning, no signal to prepare, no final moment of awareness. One instant we exist, the next everything is rewritten. What makes this concept even more disturbing is how ordinary physics predicts it, unlike many speculative theories. Vacuum decay arises naturally from quantum field theory combined with the standard model of particle physics. Though the details depend on precise measurements, the underlying framework is not fringe. It is a logical extension of what we already know, forcing us to consider that existence itself is precarious. And yet, within this terrifying scenario lies a profound question. If vacuum decay can erase everything in a blink, then what does that say about reality? Are we living inside a temporary arrangement, a cosmic bubble that only feels stable because we are inside it? If so, permanence is an illusion. The true laws of physics may not be the ones we observe, but the ones that will replace them when the bubble arrives. Some physicists take comfort in the possibility that even if vacuum decay is real, the timescales involved are vast. The half-life of our vacuum could exceed the lifetime of stars, galaxies, and black holes combined. In this view, we are safe for unimaginably long epochs, but others argue that the probability, however small, cannot be dismissed. The universe may be robust against collapse, but it is not invulnerable. This fragility alters our perspective on cosmic order. Instead of a universe built on unshakable foundations, we inhabit a system balanced on chance, where the stability of the vacuum itself is a contingent fact. It raises unsettling philosophical questions. If reality is so fragile, does permanence mean anything at all? Are we simply lucky occupants of a vacuum that has not yet collapsed? And if it does collapse, does that event mark the end of everything, or simply the end of our particular version of physics? Some theoretical frameworks attempt to soften this terror. In multiverse models, for example, vacuum decay could be seen as a transition between universes, with our bubble giving way to another domain of existence. From this perspective, reality does not end but changes form. What disappears is not the cosmos itself, but the familiar patterns that allow for life, consciousness, and order. Still, for us, that distinction offers no comfort. From our vantage, the result is absolute erasure. The notion of vacuum instability underscores a larger theme that runs through quantum physics. Reality is not what it seems. Beneath the appearance of stability lurks uncertainty, and beneath the fabric of space itself lies the possibility of collapse. The same quantum fields that allow atoms to exist and galaxies to form also carry the seeds of destruction. It is as if the universe carries within itself a built-in expiration mechanism, not tied to entropy or cosmic heat death, but to the very instability of its foundation. In confronting this idea, we are forced to accept that certainty is never absolute. Physics does not promise permanence, only probabilities. Our continued existence is not guaranteed by the strength of matter or the persistence of stars, but by the delicate balance of quantum fields. The vacuum that surrounds us is both cradle and threat, nurturing existence while holding the power to erase it without notice. For centuries, machines have followed one unshakable rule: classical logic. Every calculation performed by an abacus, a mechanical clock, or a modern silicon chip obeys the binary certainty of ones and zeros. Classical computing is deterministic, built upon the principle that each step follows cleanly from the last. But quantum mechanics has never respected such certainty. Instead, it thrives in paradox superpositions, entanglement, and probabilities that only resolve when measured. The birth of quantum computing represents the first time humanity has attempted to harness these paradoxes deliberately, to build devices that use contradiction as fuel. At its core, a quantum computer operates on qubits instead of classical bits. A classical bit can exist in only two states, 0 or 1. A qubit, however, can exist in a superposition of both states at once, weighted by probabilities. This means that while a classical computer must choose one path through a calculation, a quantum computer can explore many paths simultaneously. The result is exponential growth in potential computing power. provided the system can be controlled and the interference from the environment suppressed. But what makes quantum computation so unsettling is not just its speed. It is the way it achieves results by exploiting the very features of reality that defy logic. Entangled qubits, for example, share correlations so deep that measuring one instantly affects the other, even across distance. This allows quantum algorithms to operate in a space where classical causality seems broken. Superposition enables the machine to hold conflicting answers at once, collapsing them only when the computation concludes. The paradoxes that once baffled physicists become tools of engineering. One famous demonstration of this power is Shor's algorithm, which allows a quantum computer to factorize large numbers exponentially faster than any classical machine. Factoring is not just an abstract problem. It underpins modern encryption. The security of online communication, banking, and digital identity rests on the assumption that factoring enormous numbers is computationally impossible in practice. A fully functioning quantum computer running Shor's algorithm would render much of today's encryption obsolete overnight. The stability of global digital infrastructure depends on a barrier that quantum logic is poised to dissolve. Another striking example is Grover's algorithm, which can search through vast databases far more efficiently than classical methods. In principle, this means quantum machines could sift through oceans of data with uncanny speed, finding patterns invisible to traditional systems. Combined with machine learning, this ability could create predictive models so powerful they verge on oracular. Patterns in human behavior, financial systems, even biological processes might be laid bare. Their secrets extracted not through brute force, but through the exploitation of quantum paradox. Yet the dangers go beyond cryptography and data analysis. Quantum computers, if scaled to global power, might allow us to simulate quantum systems themselves. This would mean accurate modeling of molecules, reactions, and even new materials that defy classical chemistry. It could revolutionize medicine, energy, and engineering, but it could also yield weapons of unimaginable potency. The ability to design matter at the quantum level would blur the line between natural and artificial, potentially giving rise to technologies beyond our ethical frameworks or safeguards. More disturbing still is the philosophical implication. If quantum computers rely on paradox on particles being both here and there, on information existing in multiple contradictory states, then what does it mean when such machines succeed? Does it confirm that reality itself is built upon contradictions? If the universe can be manipulated through the deliberate use of paradox, then the boundaries between logic and illogic collapse. Human reasoning evolved to navigate a predictable world. But quantum computation hints that the true fabric of reality is not bound by consistency. Some thinkers worry about unintended consequences. The very act of running quantum algorithms may interact with the fundamental structure of probability. Entanglement and superposition are not just abstract ideas. They are features of the physical world. A massively entangled quantum computer might, in principle, affect correlations far beyond its immediate environment. Though speculative, this raises eerie questions. Could a quantum computer of sufficient scale influence probabilities in the wider universe? Could it shift the odds of events, not by calculation, but by entangling reality itself? Another unsettling aspect lies in the concept of measurement. A quantum algorithm only produces a definitive result when measured, collapsing superpositions into one outcome. But until then, the computation exists as a cloud of possibilities, many of which will never be observed. In some interpretations of quantum mechanics, those unobserved possibilities are not lost but realized in parallel universes. If so, then running a quantum computer is not merely solving problems. It is creating branches of reality where every possible outcome unfolds. To compute is to generate new worlds, each one shaped by paradox. The ethical dimension of such power cannot be ignored. If governments, corporations, or individuals were to control machines that can crack encryption, redesign matter, and perhaps even alter probabilities, the balance of power on Earth would shift irreversibly. Nations that fall behind in quantum technology may find themselves vulnerable to manipulation, espionage, or coercion. The concentration of such power in the hands of a few could destabilize societies and redefine geopolitics. Unlike previous technologies, quantum computing does not simply scale existing abilities. It transforms the rules by which information and reality are structured. And yet, despite these dangers, research accelerates. Laboratories across the world are racing to increase qubit counts, reduce error rates, and stabilize coherence times. The promise of unparalleled computational power drives investment, innovation, and competition. In this race lies a paradox of its own. To unlock quantum power, we must embrace uncertainty. The machines require shielding from noise, yet they thrive on ambiguity. They demand precision engineering, yet they operate on principles that resist determinism. To build a quantum computer is to build a device that lives on the edge of certainty and chaos. If quantum computers succeed on a global scale, we may face a new epoch of humanity, one where paradox is no longer confined to the realm of theory, but woven into the tools of everyday life. Our phones, our transactions, our security, even our understanding of science could all become entangled with devices that run on principles alien to classical logic. We would live in a world where paradox is no longer an anomaly, but the operating system of civilization. Some thinkers worry about unintended consequences. The very act of running quantum algorithms may interact with the fundamental structure of probability. Entanglement and superposition are not just abstract ideas. They are features of the physical world. A massively entangled quantum computer might, in principle, affect correlations far beyond its immediate environment. Though speculative, this raises eerie questions. Could a quantum computer of sufficient scale influence probabilities in the wider universe? Could it shift the odds of events, not by calculation, but by entangling reality itself? Another unsettling aspect lies in the concept of measurement. A quantum algorithm only produces a definitive result when measured, collapsing superpositions into one outcome. But until then, the computation exists as a cloud of possibilities, many of which will never be observed. In some interpretations of quantum mechanics, those unobserved possibilities are not lost, but realized in parallel universes. If so, then running a quantum computer is not merely solving problems. It is creating branches of reality where every possible outcome unfolds. To compute is to generate new worlds, each one shaped by paradox. The ethical dimension of such power cannot be ignored. If governments, corporations, or individuals were to control machines that can crack encryption, redesign matter, and perhaps even alter probabilities, the balance of power on Earth would shift irreversibly. Nations that fall behind in quantum technology may find themselves vulnerable to manipulation, espionage, or coercion. The concentration of such power in the hands of a few could destabilize societies and redefine geopolitics. Unlike previous technologies, quantum computing does not simply scale existing abilities. It transforms the rules by which information and reality are structured. And yet, despite these dangers, research accelerates. Laboratories across the world are racing to increase qubit counts, reduce error rates, and stabilize coherence times. The promise of unparalleled computational power drives investment, innovation, and competition. In this race lies a paradox of its own. To unlock quantum power, we must embrace uncertainty. The machines require shielding from noise, yet they thrive on ambiguity. They demand precision engineering, yet they operate on principles that resist determinism. To build a quantum computer is to build a device that lives on the edge of certainty and chaos. If quantum computers succeed on a global scale, we may face a new epoch of humanity, one where paradox is no longer confined to the realm of theory, but woven into the tools of everyday life. Our phones, our transactions, our security, even our understanding of science could all become entangled with devices that run on principles alien to classical logic. We would live in a world where paradox is no longer an anomaly, but the operating system of civilization. Skeptics argue that the brain is too warm and noisy for delicate quantum effects to survive. Quantum coherence, they note, usually requires extreme isolation and near absolute zero temperatures, as seen in quantum experiments or computing devices. Yet recent discoveries challenge this assumption. Evidence of quantum phenomena has been found in biological systems such as photosynthesis, where energy transfer in plants appears to exploit quantum coherence. Birds, too, may navigate using entangled particles sensitive to Earth's magnetic field. These findings suggest that nature is capable of sustaining quantum effects even in warm, messy environments. If the brain operates in similar ways, then consciousness could indeed be quantum at its core. This would explain why subjective experience feels so unlike mechanical computation. A classical computer processes inputs and outputs with no awareness of its own operations. A quantum conscious mind, by contrast, might directly participate in the indeterminate dance of reality, weaving probability into lived experience. Awareness could be the very act of collapsing quantum superpositions. Each decision and perception a crystallization of one path among many. The implications of such a view are staggering. If consciousness is quantum, then it may not be limited to the human brain. Other systems capable of supporting quantum coherence, whether biological or artificial, could also host awareness. This raises profound questions about the future of technology. Could advanced quantum computers one day awaken not simply as machines that compute, but as minds that experience? Would such an intelligence be alien or familiar? Would it share in the universal field of consciousness? Or would it carve out a perspective all its own? There is also the question of mortality. If awareness is a ripple in a larger quantum ocean, then death may not be the absolute end of consciousness, but rather the dissolution of a localized pattern. Just as waves vanish back into the sea, the individual self might dissolve into the broader field. This does not guarantee personal immortality in the way religions promise, but it reframes death not as annihilation, but as reintegration. Consciousness, in this sense, would be as fundamental as space-time, not generated by matter but coexisting with it. Equally provocative is the possibility that consciousness influences reality itself. Quantum theory already suggests that observation plays a role in collapsing probabilities into definite outcomes. If observation is tied to consciousness, then awareness is not merely passive but active in shaping the universe. Every perception, every choice, might contribute to the structure of reality at the deepest level. The act of being aware would carry cosmic weight, linking the personal to the universal. However, such ideas remain speculative. The scientific community is divided, with many dismissing quantum consciousness as unnecessary or unprovable. They argue that neuroscience will eventually explain awareness in purely classical terms, without invoking quantum mysteries. Yet the problem remains. No classical model has bridged the gap between neural activity and subjective experience. Until that gap is closed, quantum theories of consciousness remain on the table, unsettling in their implications, but compelling in their potential. If consciousness is indeed a quantum field, then reality itself may be richer and stranger than we ever imagined. The mind would not be an isolated organ trapped in a skull, but a gateway into the fundamental processes of the universe. Our perceptions, choices, and awareness would be not illusions or byproducts, but central expressions of the quantum fabric itself. Reality, in this view, is not something outside of us. It is something we participate in creating, moment by moment. This vision suggests that the ultimate paradox is not found in particles or equations, but in ourselves. We are quantum beings, ripples in an ocean without shore, simultaneously limited and infinite, local and universal. Consciousness, far from being an evolutionary accident, could be the deepest truth of existence. The universe is strange enough when treated as physical reality, yet quantum mechanics introduces puzzles that resemble something else entirely: the behavior of a programmed system. The simulation hypothesis takes this idea seriously, proposing that what we experience as reality might be an advanced form of computation, constructed by intelligences beyond our comprehension. While this might sound like science fiction, the unsettling truth is that certain aspects of quantum physics align eerily well with the idea of a coded universe. At the heart of this hypothesis lies the recognition that our world is quantized. Energy, matter, and even space-time itself come in discrete packets. Unlike a smooth, infinitely divisible continuum, the quantum world functions with smallest possible units, as if reality were pixelated at its foundation. Planck length and Planck time represent absolute minimum scales, below which physical laws lose meaning. To anyone familiar with computer graphics, this echoes the limits of resolution in digital simulations. Just as a video game world is composed of finite pixels and frames, our cosmos seems to operate with fundamental quanta, the smallest units of reality's code. Quantum unpredictability deepens the analogy. In a deterministic universe, outcomes could be calculated perfectly if we had enough data. But at the quantum level, certainty disappears, replaced by probability. The system does not reveal an outcome until it is measured, echoing the way a simulation renders only what the player sees. Behind the screen, nothing is fully resolved until it is required. Quantum physics mirrors this mechanism. The act of observation forces the universe to reveal one possibility, collapsing a wave of probabilities into a single experience. Some experiments strengthen the suspicion that reality may not be what it seems. Consider delayed choice quantum eraser experiments, where particles appear to retroactively adjust their behavior depending on how we measure them. It is as though the system is optimizing, selecting an outcome consistent with both present and past, as if recalculating frames in real time. If reality were an underlying program, this is exactly how it might behave, updating the record to maintain consistency for the observer. Error-like phenomena in physics also raise eyebrows. The fine-tuning of universal constants, for example, seems improbable. Gravity, electromagnetism, and the strong and weak nuclear forces all fall into extremely narrow ranges. If even slightly different, stars would not form, chemistry would collapse, and life would be impossible. In a programmed environment, this fine-tuning could be interpreted as deliberate calibration, parameters set to sustain the simulation. The universe works, not by chance, but by design coded into its laws. The simulation hypothesis gains further weight from the nature of information in physics. Increasingly, scientists see information not just as a property of matter, but as the fundamental building block of reality itself. Black hole research shows that information is never destroyed, only transformed. Quantum information theory treats bits-qubits as the essence of existence. A universe built on information sounds less like materialism and more like software running on an unimaginably powerful system. The question becomes, who or what is running it? Critics argue that such reasoning risks falling into metaphor, mistaking resemblance for explanation. Just because the universe shares features with simulations does not prove it is one. After all, mathematics itself produces patterns that can look artificial yet arise naturally. Still, the parallels are difficult to ignore. For example, quantum entanglement, where two particles remain linked across space and time, resembles non-local communication inside a computer system, where distant elements can share data instantaneously because they are part of the same underlying structure. If the simulation idea holds, then quantum paradoxes are not bugs but features. They reveal the rules of the system, constraints placed on how reality renders itself. Uncertainty ensures variability, preventing predictable determinism that could make the simulation too rigid. Entanglement preserves coherence across vast distances, like maintaining consistency across distributed processors. The limits of the speed of light resemble bandwidth restrictions, setting a maximum rate at which information can transfer. Each of these supposedly fundamental laws could be read as engineering choices. What would it mean if we truly are code? First, our understanding of existence would be overturned. Physical matter would not be ultimate reality, but an interface, like pixels on a screen, generated by deeper computational processes. Consciousness might not arise from matter at all, but instead act as the observer within the program, capable of perceiving and interacting with the rendered environment. Second, free will and destiny would take on new dimensions. Are our choices pre-coded? Or do we have the capacity to alter the system from within? Could awareness itself be a kind of input the simulation responds to? Some theorists go further, speculating that the simulation may not be perfect. Quantum randomness, vacuum fluctuations, and dark matter could be signs of imperfections, glitches in the code, or placeholders where the system has not fully resolved the underlying mechanics. Cosmic microwave background radiation, the faint echo of the Big Bang, might even represent a system-level artifact, like the static of a rebooted machine. If so, reality is not just mysterious. It is designed, constrained by the architecture of an invisible system. The simulation hypothesis is not without existential weight. If reality is programmed, who or what programmed it? Advanced civilizations, gods, or even descendants of humanity are all candidates in speculative discussions. But the more disturbing possibility is that the programmers themselves are unreachable, existing outside the boundaries of our simulation. For us, their world would be as inconceivable as quantum fields are to ants. We might be self-contained, unable to step beyond the coded walls of existence. Yet paradoxically, the very quantum strangeness that fuels the simulation hypothesis might also offer clues about how to test it. Some physicists suggest looking for limits in cosmic rays that indicate a grid-like structure beneath space-time, a sign of discretization at fundamental scales. Others propose that anomalies in quantum randomness could be hints of external interference, like echoes from the system that runs us. If such evidence were ever discovered, humanity would face the most profound revelation in its history, that the universe is not the ultimate reality, but a constructed environment designed with intent. Even if unprovable, the hypothesis reshapes how we approach existence. It collapses the distinction between science, philosophy, and theology, suggesting that our reality is simultaneously physical, informational, and perhaps purposeful. It makes paradoxes meaningful, not as flaws in our theories, but as signals pointing toward the deeper rules of the system we inhabit, and it forces us to reconsider what it means to be conscious, aware, and alive within a world that might not be what it seems. In this vision, the glitches of quantum physics are not accidents, but the handwriting of the code itself. Every particle, every fluctuation, every uncertainty carries the whisper of a deeper order, an architecture hidden beneath the surface of reality. Whether or not we ever break free from its boundaries, the possibility alone changes how we see ourselves. Not merely organisms in a vast, indifferent cosmos, but participants inside a reality with structure, design, and limits written into its foundation. Beneath the surface of all known physics, there is growing suspicion that reality itself is not built from matter or energy, but from something more elusive. Information. Not ordinary information, like the symbols in a book or the zeros and ones inside a computer, but quantum information patterns encoded in the smallest possible states of the universe. The idea is that everything we see, from galaxies down to subatomic particles, emerges from an invisible script, a hidden language that dictates how reality unfolds. This perspective represents a shift in how we think about the cosmos. Classical science described the universe in terms of matter moving through space and time. Then quantum mechanics revealed that probabilities, uncertainty, and entanglement sit at the foundation. But in recent decades, physicists have begun to argue that information is even more fundamental than matter or probability. Reality, they say, is the output of a quantum code written not in particles or waves, but in the rules that govern how they interact. Evidence for this view comes from diverse areas of research. One of the strongest hints arises from black hole physics, when Stephen Hawking demonstrated that black holes radiate energy and eventually evaporate. It created a puzzle. What happens to the information about everything that fell inside? For years, it seemed that black holes destroyed information, violating one of the most basic laws of physics. But later discoveries suggested the opposite, that information is not lost, but somehow preserved in subtle quantum patterns on the event horizon. This led to the startling realization that the fabric of reality might be best described as information encoded in surfaces, a principle known as holography. The holographic principle proposes that everything within a volume of space can be represented by data inscribed on its boundary. In other words, the three-dimensional world we experience could be the unfolding of information stored on a two-dimensional surface. This concept echoes the workings of a computer, where complex digital realities emerge from underlying lines of code. What we perceive as solid, continuous, and material may simply be the projection of deeper informational structures that remain hidden from direct view. Quantum mechanics itself reinforces this outlook. Superposition, entanglement, and uncertainty can all be interpreted as behaviors of information rather than mysterious quirks of matter. When a particle exists in multiple states at once, it is not undecided. It is carrying overlapping information. When two entangled particles remain connected across vast distances, what links them is not a physical tether, but shared quantum information that transcends space. Measurement, then, is not the act of forcing reality into existence, but the reading of a line of code, a retrieval of specific information from a universal database. Some researchers now describe the universe as a giant quantum computer. Instead of being programmed in binary, this cosmic machine operates in qubits, capable of representing many possibilities simultaneously. Every interaction, every exchange of energy, every shift in state is a calculation. The laws of physics are the rules of processing, algorithms that dictate how the code executes. Time itself might be nothing more than the progression of quantum computation. Each moment, a new step in the universal calculation. This vision radically alters how we interpret paradoxes. Instead of flaws in our theories, quantum mysteries become clues to the deeper logic of the code. The uncertainty principle is not chaos. It is compression, a way of storing maximum information in minimal space by preventing us from knowing everything at once. Entanglement is not spooky action. It is efficiency, a way for the system to maintain coherence by linking data across vast distances. Even randomness may not be truly random, but a form of pseudorandom generation, ensuring variability while following hidden rules. If the universe is written in a quantum language, the question arises, can we learn to read it? Quantum information theory is beginning to provide a grammar. Instead of treating particles as objects, it treats them as carriers of bits, units of encoded reality. By studying how these bits combine, transform, and preserve themselves, scientists hope to uncover the syntax of the universal script. Already, insights from this field are being applied to quantum computing, cryptography, and teleportation experiments, suggesting that mastery of the code could unlock unprecedented control over reality itself. But there is also a philosophical weight to this idea. If existence is governed by a hidden code, then matter and energy are illusions, interfaces built to express information in a way that conscious beings can experience. This makes consciousness itself an intriguing puzzle. Are we simply readers of the code, decoding reality as it unfolds? Or are we active participants, somehow entangled with the script, able to shape it by the act of observation? If the latter, then consciousness may not be a product of matter at all, but a fundamental part of the quantum language, inseparable from the code it perceives. The hidden script may also explain why the universe appears fine-tuned for life. The constants of physics are not arbitrary. They are parameters of the code, values chosen to sustain a reality capable of complexity. Whether these parameters were set by chance, necessity, or design is unknown, but their existence points toward structure rather than accident. The cosmic code seems written with precision, as though the universe were not just a machine but a meaningful program. Some thinkers suggest that decoding this script could allow us to glimpse realities beyond our own. If our universe is a manifestation of quantum information, then alternative realities may simply be other expressions of the same code, parallel branches where different parameters or initial conditions play out. Multiverse theories and many worlds interpretations could all be viewed as outcomes of the hidden language, multiple verses in the same grand text. What makes this idea so powerful is that it unites physics, computation, and philosophy. It bridges the gap between abstract mathematics and tangible experience, showing how bits of information can build worlds, consciousness, and even the flow of time. It reframes existence as something neither purely material nor purely mystical, but informational at its core. The code is not visible to us, but its effects surround us everywhere, in the stability of atoms, the coherence of light, the balance of forces, and the mysteries of entanglement. To live in such a universe is to inhabit a text written in an unknown alphabet. Every scientific discovery is not just a revelation of physical law, but a translation, a decoding of one more line in the script. And while we may never uncover the full language, each glimpse reshapes how we understand ourselves, not as passive spectators in a mechanical cosmos, but as conscious readers woven into the code of reality itself. The deepest question in physics is not how the universe works, but why there is a universe at all. For centuries, humans assumed the cosmos had a starting point, an origin where matter and energy came into being. The Big Bang Theory gave this idea scientific weight, placing a beginning about 13.8 billion years ago. But quantum mechanics has revealed a possibility that undermines the very notion of beginnings. The universe may have created itself, a paradox that denies both external causes and absolute origins. To understand how this could happen, we must revisit the quantum vacuum. In classical terms, a vacuum is empty space, devoid of matter and energy. But quantum theory tells us that no space is ever truly empty. Instead, it seethes with fluctuations, pairs of particles flickering into and out of existence faster than we can measure. These fluctuations are not random intrusions. They are required by the uncertainty principle. At the smallest scales, nothingness itself becomes unstable, continually generating virtual energy. Now imagine a fluctuation so massive that it does not simply vanish back into the void. Instead, it inflates, grows, and stabilizes into an entire universe. The laws of quantum mechanics allow this scenario, because the total energy of a universe might add up to zero. The positive energy of matter balanced exactly by the negative energy of gravity. If that balance holds, a universe could emerge without breaking conservation laws. In this view, existence requires no external spark, because the math permits the cosmos to be its own origin. This possibility redefines creation. Instead of asking what existed before the universe, quantum physics implies there may be no before. Time itself could be a product of the expansion. emerging alongside space. The origin paradox dissolves, not with a divine act or a physical cause, but with a loop where the universe births itself through the interplay of quantum rules. It is not so much an event in time as it is the boundary where time and space themselves begin to exist. The self-creating universe is not just theoretical fantasy. Certain models of cosmology, such as quantum cosmogenesis and Hartley-Hawking no-boundary proposals, show how a universe can emerge smoothly from quantum fields without requiring an initial singularity. In these models, the Big Bang was not a literal explosion, but a transition, the moment when potential condensed into reality. The universe, in effect, tunneled out of nothing, sustained by the same quantum probabilities that allow particles to cross barriers they should not be able to cross. This paradox challenges the human mind because it defies causality. We are used to causes preceding effects, to the idea that every event follows from something else. But at the quantum level, causality is not absolute. Events can be uncaused, determined only by probabilities. If universes can self-create, then reality itself may be the ultimate uncaused phenomenon. The cosmos is both question and answer, a closed loop of being that does not depend on anything beyond itself. It is here that quantum mechanics and philosophy collide. Some argue that this vision is unsatisfying because it does not explain why quantum rules exist in the first place. Why should there be laws that allow universes to emerge spontaneously? Others respond that this is the wrong kind of question, because laws are not imposed from outside. They are intrinsic to reality, as fundamental as mathematics itself. Asking why they exist is like asking why numbers exist. The code does not need a programmer, it simply is. The notion of self-creating universes also connects to the idea of a multiverse. If quantum fluctuations can spawn one universe, there is no reason to think they cannot spawn many. Each fluctuation could give rise to a new cosmos, each with its own physical constants and structures. Our universe, with its galaxies, stars, and life, may be only one bubble in an infinite froth of reality. In such a landscape, paradox is not an anomaly, but the rule and endless process of universes emerging, evolving, and disappearing. But even if countless universes exist, the paradox remains intact. Each one still originates without external cause, each sustained by its own balance of quantum energies. Together, they form a tapestry with no beginning and no end, a structure that is always generating itself. This is the ultimate paradox. Existence without foundation, creation without creator, reality as its own explanation. For human beings, this concept is difficult to accept because it strips away the comfort of origins. There is no first cause, no initial condition imposed from outside, no reason in the conventional sense. The universe is not something that began. It is something that perpetually exists through the mechanics of its own rules. To live in such a cosmos is to accept that the deepest truth may not be why reality exists, but simply that it does, arising from the paradoxical marriage of nothingness and quantum law. What makes this paradox so haunting is that it might be correct. Observations of the cosmic microwave background, the distribution of galaxies, and the accelerating expansion of space all fit comfortably within models that allow self-creation. No experiment can yet confirm the theory absolutely, but the pieces align in a way that suggests reality's strangest possibility may be its truest. If the universe did create itself, then every atom, every star, every thought is a ripple in a process that required no beginning. We are part of a self-sustaining cycle, a cosmos that needed nothing outside itself to exist. It is a paradox that does not weaken our understanding, but deepens it, reminding us that reality may not follow the logic of human expectation. The universe is not a story with a first chapter. It is a book with no starting page, written by the quantum rules that both contain and transcend everything we know. For as long as science has existed, Observation has been the foundation of knowledge. We measure, we record, and from these acts we build laws and theories. But in the quantum world, observation does not simply reveal what is there, it shapes it. The unsettling paradox is that by looking, we may not only be changing the outcome, but also destabilizing the very rules that hold the universe together. The first sign of this paradox emerged from the double-slit experiment. When particles such as electrons are fired toward a barrier with two slits, they behave like waves, creating interference patterns as if each particle travels through both slits simultaneously. But when detectors are placed to see which slit each electron passes through, the interference vanishes. The electrons behave like discrete particles, as if awareness of their path forces them into a single reality. What should have been a simple test turned into a revelation. Observation collapses possibilities into one. At first, this collapse seemed like a trivial detail, a quirk of measurement. But deeper investigations suggested something far stranger. The universe, at its most fundamental level, does not have definite states until observation fixes them. Reality itself appears indeterminate until interaction defines it. The act of seeing does not just uncover information. It crystallizes existence into a single version of events. Without measurement, reality lingers in superposition, suspended between multiple outcomes. This raises a disturbing possibility. If observation defines reality, then each act of looking is not neutral but constitutive. The world around us may not be a stable backdrop, but a fragile structure sustained by continuous acts of measurement. Each conscious encounter, each physical probe, each experiment forces the quantum fog to congeal into solid form. In this sense, reality exists not independently of observation but through it. Now imagine what this means for the larger cosmos. If quantum effects govern not just particles, but the fabric of space-time itself, then observation could be more than passive discovery. It could be the very mechanism that drives the universe's unfolding. But what if this mechanism is also a fault line? Each measurement erodes the multiplicity of possibilities, collapsing waves into outcomes, trimming away other realities. Over billions of years, the universe might not be building stability but consuming it, unraveling under the weight of its own observed states. Some interpretations of quantum mechanics, such as the Copenhagen view, suggest that collapse is unavoidable, a fundamental rule of existence. Others, like many worlds, argue that collapse is an illusion, and every possibility branches into its own universe. Yet both positions preserve the same troubling core. Observation is not passive. Whether it chooses one path or splinters into many, it alters the very nature of reality. In both visions, the observer is tangled within the system, unable to stand outside of it. This entanglement becomes even more haunting when applied to cosmic scales. Consider the edge of the observable universe. The light reaching us from distant galaxies is billions of years old. By observing it now, are we not collapsing states that have traveled across the span of cosmic time? If so, then our act of looking may retroactively alter events that occurred eons ago. Observation becomes not only a present act, but a rewriting of the past, enforcing consistency where only probabilities existed before. The paradox grows sharper when paired with the notion of quantum information. Every particle carries bits of data about its state, and observation forces that information into definite form. But if reality is fundamentally informational, then measurement could be seen as editing the code itself. Each observation is not just reading the script but rewriting it, patching the program of existence line by line. This leads to a chilling thought. Perhaps the universe is not gradually evolving, but being continuously rewritten by the countless acts of observation occurring everywhere, from photons scattering off atoms to conscious minds watching the sky. There are those who propose that this instability is not destructive but creative. Without observation, reality would remain an amorphous cloud of probabilities, devoid of definite form. Observation provides the boundaries, the anchors that make a coherent world possible. Yet others argue that such a system cannot remain stable forever. If observation both constructs and consumes possibilities, then eventually the system may collapse under its own paradox. Reality would not end with a bang or a freeze, but with the silent erosion of coherence itself. The unraveling of laws as observation exhausts the field of probabilities. This possibility reframes our role within the cosmos. We are not passive witnesses to a predetermined script, but participants whose very act of seeing shapes the story. Consciousness, in this view, is not a bystander, but a mechanism of reality itself. The question is whether this mechanism safeguards the universe or imperils it. If too much observation destabilizes the quantum balance, then every act of measurement could be hastening the decay of order. To observe is to erode, and the closer we look, the more fragile the structure becomes. The paradox of observation reveals the ultimate tension between knowledge and existence. We seek to understand reality, but in the act of probing, we may be unraveling it. The double-slit experiment is not just a curiosity of physics, it is a warning. It tells us that reality is contingent, that looking too closely carries risks not only of misunderstanding, but of dismantling the framework itself. At the heart of this paradox lies a question that cuts deeper than science. Is reality something that exists independently, waiting to be found? Or is it something we continuously co-create through our interaction with it? If the latter, then observation is not just discovery but construction, and every act of looking pushes the universe further along a path that may not be reversible. To accept this is to see existence itself as fragile, held together by the tension between probability and observation. It is a reminder that the more we uncover, the more we participate in the very process that may someday bring reality undone. To exist in this universe is to exist inside a contradiction. Every principle of daily life suggests that reality is solid, predictable, and consistent. We expect the sun to rise tomorrow, the ground to stay beneath our feet, and the laws of physics to operate the same way everywhere. Yet quantum mechanics whispers something entirely different. Certainty is a facade. The deeper we look, the more reality dissolves into probabilities, paradoxes, and unresolved contradictions that refuse to align with common sense. To live inside such a cosmos is to live inside a paradox, one where stability is an illusion that masks an undercurrent of uncertainty. For human beings, this realization is profoundly unsettling. Our survival instincts demand order and predictability, because only then can we plan, build, and create meaning. But the foundation of the universe undermines that comfort. On the smaller scales, particles defy singular identity, existing in multiple states at once. Observation itself changes outcomes, leaving no objective baseline. Entanglement mocks the very concept of separation, linking distant entities in ways no classical framework can explain. These phenomena are not exceptions. They are the bedrock on which all else rests, which means that our existence is not framed by certainty, but by paradox woven into the fabric of everything we are. When we face this truth, a question emerges. How do we live in a reality that refuses to be absolute? One response has always been denial. We build layers of human culture, language, science, and belief to impose order, erecting structures that hide the cracks beneath. Laws, equations, and models become shields that allow us to navigate the world as if it were coherent, even while the foundations remain contradictory. Yet no matter how elaborate our structures become, quantum mechanics waits underneath, reminding us that our sense of stability is provisional. Another response is acceptance, the embrace of paradox as part of existence itself. To accept is not to surrender understanding, but to recognize that the human desire for certainty may itself be misplaced. Reality may not owe us clarity. Instead of demanding fixed answers, we can see ourselves as participants within an unfolding system. where uncertainty is not failure, but the rule. From this perspective, paradox is not a flaw in the universe, but a signal of its deeper complexity, one we may never fully resolve but can still explore. Living within paradox also reshapes how we think of knowledge. If every observation alters what is observed, then our pursuit of truth is not about uncovering a static reality, but about engaging in an ongoing interaction. Knowledge becomes relational rather than absolute, a dance between what is and what is perceived. This does not make truth meaningless, but reframes it as something dynamic, forever shifting with context and perspective. Certainty becomes less important than adaptability, less about fixed conclusions, and more about responsiveness to an ever-shifting ground. For individuals, this carries existential weight. What does it mean if death, choice, time, and even identity are rooted in paradox? Some interpretations suggest we exist across multiple branches, our consciousness never confined to a single timeline. Others imply that awareness itself may ripple through quantum structures, suggesting that what we call the self is not as bounded as it appears. The paradox of existence, then, is not just external but internal. Each of us embodies contradiction biological machines bound by deterministic laws, yet also conscious beings experiencing freedom, continuity, and meaning in ways no equation fully captures. The paradox also touches ethics and responsibility. If reality is not singular, if choices fracture into multiple outcomes across branching possibilities, what does responsibility mean? If in one universe I succeed and in another I fail, do both outcomes matter? The paradoxical structure of existence destabilizes the clear categories we rely on, challenging the very frameworks of morality and consequence. Perhaps responsibility itself is not tied to outcomes, but to participation, the willingness to act meaningfully even when certainty is impossible. Paradox does not mean chaos. It means the universe operates on principles beyond the scope of binary logic. Quantum systems, though unpredictable in specific outcomes, still follow probabilistic rules that allow structure to emerge. Stars form, planets orbit, life arises, not because certainty dominates, but because paradox allows complexity to flourish. In this way, paradox is not the enemy of order, but its hidden foundation. Without the indeterminacy of quantum rules, there would be no creativity, no variation, no possibility for novelty. The paradox of uncertainty is the engine of existence itself. Seen from this vantage point, to live inside the paradox is to recognize that certainty is not a requirement for meaning. Meaning emerges not from absolute guarantees, but from the ongoing process of interaction, observation, and choice. The universe may be contradictory at its core, but we are part of that contradiction, and within it we carve stories, build civilizations, and seek understanding. The paradox does not negate human experience, it defines it. To live with this awareness is to stand in a place of humility. We are small creatures navigating an incomprehensible system that resists full resolution. Yet it is also a place of empowerment. To recognize paradox as fundamental is to free ourselves from the illusion that certainty is necessary. Instead, we can embrace the unknown, explore without demanding final answers, and find meaning in the very act of engaging with mystery. The paradox of the universe is not something we stand outside of. It is the fabric we are woven into, the condition that makes us possible. To live inside it is to live inside reality itself. Not the stable, orderly version we prefer, but the deeper, stranger reality that truly exists. Certainty may be an illusion, but within paradox lies both the terror and the beauty of existence. Standing at the end of this journey, we are forced to confront the question that shadows everything we have explored. If paradox is the core of reality, then what happens if it ever collapses? Can the universe, and by extension ourselves, survive when the contradictions that sustain existence are no longer balanced? This is not a simple speculation. It is the ultimate uncertainty, the edge where physics, philosophy, and human fear meet. At the most basic level, everything depends on paradox. Quantum superposition allows particles to occupy multiple states until measured. Entanglement ties distant entities together in ways that defy separation. Even the flow of time may be an illusion, with past and future bleeding into one another in ways that contradict causality. Without paradox, there is no space for probability, no room for creation, no mechanism for reality to exist as we know it, which means the paradox is not a side effect, it is the scaffolding of the universe. But scaffolding can collapse. If the laws that depend on uncertainty were to resolve into pure absolutes, the system might freeze. Without the flexibility of quantum states, particles would lose their capacity to interact dynamically. Without entanglement, the web that connects the cosmos could unravel. Without instability, time itself might cease to flow, leaving a sterile void where no change is possible. The paradox that feels so frustrating from our perspective may, in truth, be the only thing preventing existence from dissolving into nothingness. This raises a haunting possibility. Survival itself may depend on paradox continuing. If the contradictions that bind the universe ever fail, survival is not just unlikely, it is conceptually impossible. There would be no us left to endure, because the conditions for consciousness, matter, and even time would vanish in a single collapse. This is not annihilation as we imagine it, where destruction occurs within time. It is erasure of time, an undoing so complete that even the memory of existence could not remain. And yet, paradox also offers another possibility. If contradictions are infinite, then collapse may be impossible. The paradox cannot fail, because failure itself is part of the paradox. To erase uncertainty would require certainty, but certainty has no foothold in this system. The contradiction sustains itself by definition. In this sense, survival is not something we must achieve, but something already woven into the paradox itself. The very instability that frightens us may also be our protection, ensuring that reality continues precisely because it is unresolved. From the human perspective, this is where survival becomes psychological as much as physical. Living at the edge of paradox requires us to abandon the search for final answers and embrace existence as an ongoing question. If we cling too tightly to certainty, we risk collapsing under the weight of contradiction. But if we can accept paradox as the natural condition, then survival takes on a different meaning. It is not about outlasting the universe, but about living fully inside its unresolved state. What does this look like in practice? It means recognizing that our need for order, while essential for daily life, does not define the whole of reality. It means seeing our choices, our experiences, and even our fears as part of a much larger tapestry, where uncertainty is not the enemy, but the rule. It means understanding that survival is not merely biological continuation, but participation in a paradoxical cosmos that exceeds comprehension. To survive the paradox, then, is to live without demanding that it be resolved. There is also a spiritual dimension here, though not in the traditional sense of doctrine or belief. To face paradox is to confront the limits of human knowledge and to recognize that those limits are not failures, but boundaries set by reality itself. The paradox does not humiliate us, it situates us. It places us within a system so vast and strange that our very attempts to measure it alter its behavior. Survival in this context is not about overcoming the paradox, but learning to live with reverence for its depth. Some might call this surrender, but it is better described as alignment. To align with paradox is to accept that contradictions may never resolve, yet to continue searching, questioning, and creating within them. That is the essence of survival, not the guarantee of permanence, but the courage to live meaningfully in a universe that denies certainty. The edge of reality, then, is not an endpoint, but a horizon. Beyond it lies only speculation, because speculation itself becomes entangled in the paradox it tries to escape. But at the edge we find a kind of clarity. We see that existence is not about securing permanence, but about embracing impermanence. It is not about finding the final truth, but about dwelling in the unfolding contradictions that sustain all truth. Survival is not the absence of paradox. Survival is paradox itself, lived out in every breath, every choice, every act of observation that both sustains and alters the world around us. So can we survive the paradox? The answer is both no and yes. No, in the sense that there is no survival beyond the collapse of paradox, because collapse would mean the end of existence itself. And yes, in the sense that we are already surviving, because the paradox has not collapsed and perhaps never can. Our existence is the proof. We survive because paradox sustains us. We endure because contradiction is the condition of being. At the edge of reality, the final lesson is simple yet profound. We are not meant to escape the paradox. We are meant to live inside it. Our survival is not about overcoming contradiction, but about recognizing that contradiction is the very reason there is something rather than nothing. To survive the paradox is to be part of it, and that is what we have always been.